Thanks for this workshop. I think it's a this workshop is on workshop in November, and it was as sort of like popular in school. So yeah, so good workshop, the kind of petition. But anyway, that is fine. This workshop is hosted in collaboration with Rootconf, which is a company for SRD infrastructure, and now everything that is also infrastructure around the IBC and also already off the sector. As a community, and have now access to all the activities, starting from the kind of the funding, very small to trust. Their side the work. So not be into with the syllabus, but the idea is to kind of with the understand how to make it. I'd also like to thank folks who are here today. Shilpa and Sheila. Can start with one. Last time I attended a especially so that would even transformation was quite good. So that calculation got just one thing to yeah, I still get confused myself for topic. So I think today I talk about few things and we'll explore things better first. Say that we need data by certain such timestamp. And as simple as it may sound, it's one of the most tricky problems in storage and distributed. Complex ones. Uh, so yeah, yeah, and also make for the IT population. It's how you how
I am given by all the senior director of the profile. I stay at that way now. I want start some application. Someone says that I want to do a database which does this. They are primarily forced. Maybe the hard reality, but that is actually right. They are forced to use it. From the standpoint, so from the engineer standpoint, I talk about some real customer problems. The customers environment, uh, current situation, then so these days, like reality of modern applications is, I mean, any company that starts today, let's say you are starting a startup and want to do some online stuff, right? And you are an integrator. All these modern applications. So when you have this kind of applications which are distributed, your database becomes a lot. You have to so customers talk about some of the that's why they need a distributed database. People might know So, like I was saying, these days the modern applications have certain needs. Because when you start your database, so when you start a company or when you start a new application, you never start at a distribution. You start with something which is simple enough for that. This when you start with on services and cloud native architectures put a lot of pressure on the existing developers.
Okay, one. Oh, Zoom settings is it? Okay, all right. Okay, so we are in workflow settings one.
What happened?
No, we're just checking the settings. The audio is very bad for the online.
No, I think
audience.
it should be fixed now.
Uh,
It's connected to something else.
yeah, so the current is MacBook
it's-
Pro microphone. The noise cancellation, is it? For the MacBook Pro. Okay, should I go into audio settings and check?
No, it is looking.
Okay, so the speaker over here will be 1 minute. It will be Rocker 650 Pro MacBook Pro speakers. Okay, and then we'll go to the audio settings in the MacBook Pro itself. Okay. Okay, we need to, this is fine. We need to go to the settings in Zoom. Settings. Should we check in more? So, yeah. So we need to go to settings. No, where are the Zoom settings?
Share computer sound.
So share computer sound, it says off over here, and then there's mono and stereo. Okay. Okay, so this 1 minute, I'll just
Can we just keep on
just 1 minute, Unmesh, I'll just check.
Laptop.
1 second. I'll just check Unmesh. Unmesh, just one more.
Sorry.
Sorry. So where are the settings? I'm not able to see it over here. Bottom. Yeah, of course, yeah. Okay. And then there's audio. There's MacBook Pro speakers. Yeah. Okay. Then there is noise removal default. So you're saying original sound. So there are three options. There's noise removal default, there's background noise suppression, there is personalized audio isolation, there's original sound for musicians. Okay, and Background noises, yeah? Okay, all right. Okay. Original sound for musicians. Okay, all right, okay. Okay, well, hopefully this solves the problem. Okay, all right, thanks so much.
So we can start, right?
Yeah, we can start.
Can we ask them if they're able to hear? Yeah, can we check if they're able to hear?
Hey guys on live streaming, can you message if you are able to hear?
See the messages? Should we start? Yeah, I think we should start, right?
Yeah, it's much better now.
Yeah.
Okay, so I'll start from here. The reality of modern applications today is that the database has become the primary bottleneck because of all the growing needs of the applications. Okay, so let's talk a little bit about the customers, YugabyteDB customers who have faced an issue and with their current databases, and then they have moved to YugabyteDB. So let's look at each one of these customers. What kind of issues did they face, and why did they? I mean, what was the point wherein they broke and they thought that they need something different than what they have right now, or they had at that point. So Kroger, which is a large e-retailer in, or rather retailer in US, it has stores across the entire US, and they needed a always-on multi-region system, right? Because even in US you have 3 different regions, you have central, east, west, and they wanted an always-on multi-region setup wherein the data could be distributed across different regions. They tried a bunch of things just to ensure that they don't land into some kind of problem. They tried hybrid setups with multi-cloud and other infrastructure, but this all increased their downtime risks, primarily because the application became pretty complex, and the application had had to ensure that the data is always available. So the entire responsibility of data came onto the head of application itself, right? So this exposed them to a lot of downtime risks. Another customer that YugabyteDB has is Paramount Plus. Paramount Plus is a media company. One of the major events that Paramount Plus does is it's live streaming of Super Bowl event. That Super Bowl event is a very popular event in US, and it has a lot of traffic coming in. So when they were running that, they experienced a lot of latency and performance degradation, which sometimes also led to outages, right? And this was primarily during the traffic spikes time, right? For example, Super Bowl is happening and a lot of people are streaming in, they started hitting a lot of issues. So that is what one of the challenges they had. Rakuten, it's an APJ customer, it's in Japan and in other Asian countries. It also wanted, it is a telecom company, and it had its own Kubernetes infrastructure wherein it was deploying a set of services, and it wanted a database which was also distributed just like their application, so that they can have a active multi-region writes, right? They wanted to write some data here, they wanted to write in another region as well, and they still wanted to have the common copy, right? So this is a very challenging problem to solve, and this is what they wanted. Pfizer, it's a US financial company, a very large company. It does a lot of payment related processing and other things. They had this challenge of consistency versus availability trade-off, because they are processing so many number of transactions. It was hard to them with a full consistency and at always available kind of scale, right? So they thought that, they needed financial correctness at scale, and it was very hard to do. Comply advantage, this was also a very unique problem. They were able to solve all their problem of multi-region, and they were also able to solve a lot of problems related to consistency guarantees of data in multi-region environment. However, the main problem they were struggling was with, they didn't have the query layer, right? They had to use all the difficult APIs of all the NoSQL products, and they were stuck into it. So they wanted a SQL query at scale in a distributed environment, and that is why I think they came to us, right? That was one of the advantages. MindGate solutions, I think this is an interesting one and would relate to a lot of us here. MindGate Solutions is a vendor which provides a lot of softwares and tools around UPI transactions to a lot of financial companies in India, a lot of banks in India. I can't name the banks which are our customers, but MindGate Solution is the vendor which provides them the UPI transactions. So if you guys have done some transactions, UPI transactions while coming here, there is a 50% chance that they might have gone to YugabyteDB. Because MindGate is a very large customer, it is like multi-million-dollar customer for us, primarily because it is hosting, it is giving services to other banks. So MindGate, the problem was scaling payment throughput. India was growing, the digital transactions in India were going at a very rapid pace, and they were like breaking, their applications were breaking at or when they were going to the large scale. So that is why they needed a solution which could support all the UPI infrastructure that they have. Shopify, it's a recent customer that we have acquired. Shopify is like a beast when it comes to database deployment. They had like hundreds of nodes of MySQL deployment for their services. So Shopify is basically a retailer, not exactly a retailer, it provides a platform to retailers in Canada. And they are a very large company, and they had like hundreds of MySQL servers that they were running. And again, because of that, it was becoming, their applications were becoming pretty complex, and it was very hard to manage it, right? And also like the flash traffic plus global users exposed the DB limits. So these are few of the customers. These should give you an idea, like this problem is not a niche problem. It's a problem which is becoming more and more important because of the growing needs of the applications.
Yeah. One question I had on the first line. So when you say about the first line of the same slide.
First line, okay, I'm sorry. Yeah.
So when you say about the multi-region system, so it's the same database span across multiple regions or something like the replicas that we have in India?
So YugabyteDB supports both of the architecture. In this case, they had a multi-region deployment wherein the data. So think of it like this, right? We replicate the data across regions, right? So you write a copy of data, it could be replicated to all the regions. So that is one mode. Then you have, in this mode also the replicas are across the node. And then there is one node which is like the traditional mode in which you have one database here and another database here, and it gets replicated to the other side, right? Via some this CDC and the X cluster infrastructure. So Kroger is primarily a multi-region setup wherein they are keeping their primary copies of data across different regions based on their user needs.
Kind of replicating the data from US East to US West.
So the replication will happen primarily to ensure that in case of a disaster, the data is still available. However, you would like to keep the primary copy closer to your users in Okay, I think I touched upon it a little bit, but these were the original trade-offs that we had. SQL databases like Postgres and Oracle.
Yeah,
Hello.
Zainab, I think what I suggest is we go ahead with this talk.
Okay. Yeah.
And
And
then we'll take a
maybe
5-minute break and
Yeah.
fix it.
Okay. All right. Yeah. Okay. We can go back to the presentation, and then maybe we can share the slides with the online audience.
So there is
So I think given the customers or applications that were facing the problem, this is what their challenge was, the trade-offs that they were dealing with. If they go to a SQL database like Postgres, Oracle, MySQL, they were getting very strong consistency, they were getting all the SQL queries, they were able to write a lot of easy logic because it was all SQL queries, but the database was hard to scale, and eventually when they were creating multiple instances of the database, all the responsibilities of sharding the data or owning that entire infrastructure came down to them, right? While at the same time, they could have moved to NoSQL databases like we saw in case of Comply Advantage. They had a NoSQL database which was giving them massive scale plus high availability, but it had NoSQL support, right? Cassandra, DynamoDB have challenges with databases, with transactions as well. MongoDB although supports transactions, but it has no SQL support. So this SQL challenge is a big challenge from a application perspective, because a lot of application developers are very like they know SQL much better than any other language, right? So that is why SQL is an important aspect. So today, before YugabyteDB, they had to choose. They could never get both, right? So they had to choose between these two trade-offs. Now, what customers actually needed, right? I mean, you might have already guessed it. I don't have to tell it explicitly. They wanted a PostgreSQL, but distributed, right? That is why I think YugabyteDB came into picture. You want horizontal scalability. You want strong asset guarantees. You want multi-region distribution, and you don't want to lose much on the latency, right? And SQL, definitely, that is something that most of our users want, right? So this is what is the distributed SQL promise. You get SQL at scale. You get SQL with all the asset guarantees. You get SQL with all the multi-region properties of the data. Yeah.
Across region, YugabyteDB does strong consistency, right? Or it's like async replication?
So both, like I was explaining earlier, both of the modes are supported. We write in a synchronous manner as well as we have the async replication as well. When you write synchronous replication, you have to be aware that there will be region latencies that will be applicable. But still, I mean, a lot of our customers also want that kind of thing, because with a different various forum kind of thing, you can achieve multi-region synchronous writes.
In terms of data loss as well, right? I mean, that's
yeah, data loss is something that is on the top of our mind as well, and we design for that. So yeah, even in case of a failure, we ensure that there is one copy available of data at any point, at any given point in time. So if you have 3 different regions, the data will be available definitely in 2 of those regions, so that the data is available most of the time.
Yeah, but if customer chooses async, then in that case, do you think?
So that is a lot of, like for example, I will give you an example. RBI has mandated all of our banks here in India to have this data across 2 regions. India only has 2 regions right now. So most of our banks are going with that async replication with Yugabyte, right? So you have data in one region and this thing. So this is a requirement that is coming from that we want to have the data here in 2 different regions. So that is the question, right? Whether we are, so what was the question? Sorry again.
I was coming from S3 as object storage, right? Where they have multi-region, strong consistency, right?
Correct.
And they have this 11.9 support when, let's say, some region goes down.
Yes.
I'm not sure how they arrived to that number, but similar capabilities are there.
Yeah, so S3 is an object store, right? While this is a database. So again, when you are writing to S3, you are dealing with a file system kind of infrastructure. It's the same discussion whether you always had Linux, why did you want an Oracle database, right? So similarly, you have S3, but you will still want YugabyteDB or a similar product, right?
There is an online question.
Yeah.
So is the replication across regions multi-leader?
You can repeat the question.
So the question is the multi-leader replication across regions solved it. So when you say multi-leader, I assume that the data, so leader, I will talk a little bit about this. You have the data in Yugabyte is sharded into tablets, right? And when the data is sharded into the different tablets, each tablet has got a leader and 2 followers, right? So you can have some data in a particular zone, leader of a data in a particular zone, and another leader in another zone. So for example, if your data is divided by, let's say all the Pune users' data is in Pune zone, while or maybe in India zone, while for all the San Francisco users' data is in US West 2 zone, right? So the leaders will be different, but the followers will be distributed across everywhere, right? right? So this multi-leader thing, there is no replication amongst the leaders themselves. The leaders replicate the data to their followers, and the leader and follower deployment topology helps us solve this problem. If
So
that
does
answers
leader
the
also is replicating data across the region?
question.
Because
Leader,
you just said.
so leader is the
director-
primary entity which will replicate the data across the regions. So leader is the node who is getting all the writes. When it gets the write, it says that, okay, I will have to send it to all the followers. And it will ensure that a write is committed only when a quorum is achieved, and quorum is like n by 2 plus 1 votes.
Okay, let's say some customer enables the mode, he wants multi-region from consistency, right?
Mhm.
Which Yugabyte guarantee. I think.
That is the only mode we support.
Okay, that is the only mode you
That is the
support.
only mode we
So
support.
leader has to write the data within the cluster, whatever inching replica that has, whatever the quorum it has to meet. It also has to write data across the region, it sits in the different zones.
Yeah, so the quorum, the across region is part of the quorum itself, right? For the mode where you have, right, multi-region mode, when we have the synchronous write, the node in the other region is part of our quorum. And when we write the data to our leader ensures that, let's say your nodes are in US West, US East, and US West 2 maybe, right? So if you have these three regions and you write data to US East will ensure that out of these two regions, it has written to at least one region before saying that, yeah, the write is committed.
Okay, so leader, replica could be from any region, that's what you are saying, and leader.
So the follower replica, the followers could be in any region.
Okay.
You will always have the deployment topologies to configure them. You can say that I want my leader here and my followers here, just to make your application fast.
Okay. And what happens if leader goes down? How the leader election happens?
So that is something that Umesh will cover as part of his raft.
those details.
Oh,
Yeah.
okay, sure, thanks.
Yeah, so Umesh will definitely cover that, but it's the raft technology
Okay.
that we use it.
One question. So on this slide, so did you have customers who came to you who had tried Citus in this context, like basically the previous slide, right? Like Postgres, what they had to do distribution. When I say they, it basically means that the application layer had to be aware of the distribution.
Correct.
So did you have customers who came who tried Citus and then still said that maybe that Yugabyte works better for us?
Yeah, so Citus, I am not sure exactly if there was any customer who directly came from Citus. Our primary customers are coming from Aurora, right? So Aurora is something that I can talk about, because in Aurora you have storage that gets replicated, right? Something similar might have happened in Citus as well, right? But I don't know exactly.
Citus is an extension. But
yeah.
Okay, I mean,
yeah, so the Aurora are most of the customers because the consistency guarantees that they need at the database level. Right? So not at the storage level, because you can't guarantee whether a transaction is fully written or not. At the storage level, you only can guarantee that at the database level. So you need a database which can guarantee that thing at the database level.
Sorry.
Yeah, sorry.
I just want to understand at a high level, what is the difference between the Apache Ignite and this? Of course, this is a SQL and NoSQL, but or GridGain or Apache.
So I can talk about GridGain. GridGain was one of the competitive products in my previous company, Gemfire. So GridGain is an in-memory key value store.
But they also support the assistance on disk as well.
Yeah, but they are the kind of a key value store. So when I say key value store, it is not a SQL environment.
That's what I'm saying.
Right? It's not. So that is one of the primary.
But I think Ignite does support the SQL like a query as well.
Yeah, can we park these questions?
Okay,
maybe?
for you.
Yeah, this is
Yeah.
Okay, so I think I talked already about it. I will not go in detail. So the core idea is you have a SQL interface with distributed system underneath, which supports sharding, replication, and transactions. So these are the key YugabyteDB features. This is one marketing slide that I will use here. So one of the key features that we have is the PostgreSQL compatibility, right? Because PostgreSQL suddenly, I mean, it was a chance that we picked up PostgreSQL as our query layer, and PostgreSQL suddenly became very popular, right? We had a choice, MySQL or Postgres, and for some reason there was no real thought about it, but we picked up Postgres, and it is luck, right? That PostgreSQL compatibility, and now it has become a top feature for us, because now what we can say is that any application that you are running on Postgres, bring it to Yugabyte when you need scale, right? So you are hitting all the issues with your Postgres infrastructure, bring into Yugabyte, it will work, your application will work as is, and you will get all the benefits of horizontal scalability, strong consistency, multi-region support, and the fault tolerance, right? So that PostgreSQL compatibility, everywhere you will go at Yugabyte, we'll try to call it as Postgres, distributed Postgres, or something like. These are things that we discuss internally as well, whether we should call it Postgres, distributed Postgres, or something else. But this is one of the key important feature of Yugabyte, which also differentiates it amongst its competitors directly. Again, I will not go into detail here, but this is related to some of the questions that were, how am I doing on the time?
We'll cover this.
Yeah, we'll cover this in that detail, but I think there were some questions that were coming in which can say that, yeah, you have an app which is writing the data, you have a transaction manager in between, which is writing to the tablets, right? So these are the tablet leaders. I think there was a question somewhere from tablet leaders. So these are the two tablet leaders, and this data gets distributed across the different followers. Right? So that when the request comes in, it runs on the data that is automatically sharded, and the rows are split into these tablets, and that single transaction can touch multiple different tablets. And then the transaction coordination begins here. I think Umesh will walk you through the details of how this exactly is working, the transaction coordinator. And this transaction coordinator ensures that the distributed transaction is replicated in a consistent manner and in an orderly manner as well. Yeah, so this is again in continuation to that. Again, I will not go into the detail of it, but writes, the writes use raft replication. When you write to a particular node, it uses raft replication to write the data to all the followers and ensure that you get a number of quorums sent back that, yeah, we have written the data. Then you have two-phase commits that are used for doing the distributed commits, right? You have a prepare phase and a commit phase. This guarantees the atomicity across the nodes, right? That is an important aspect, because this, current databases like Postgres or these guys have an easy life because the transactions have to be run primarily on the same node, and they could use all the benefits of the logs and everything. But as soon as you go to a distributed node, you can't use those in-memory logs, and you will have to write the data somewhere to make sure that there is a logging and that you ensure that the data is written in a timely fashion. And the last point, which is very important and which primarily Umesh is going to cover, is the time ordering with the hybrid logical clocks. Right? This is an important aspect. You are doing a transaction, you need to ensure that the data is written not only in a consistent manner, but is also in an orderly manner. Right? One transaction that has started before should see the right snapshot of the data, and this transaction should also be committed, just serialized along with the other transactions. Right? That is what the database has to do. It has to ensure that all the transactions are committed in a serial order.
Sorry, just to place the terminal, you used it before also. So tablet is used in the sense of a partition.
Tablet
is
is
a logical partition.
Correct. So you have table and you have tablets. It's not a logical partition. I will call it a physical partition, because it's a physical. It's entirely different. Tablet is an entirely different. It's object. It has a file system metadata associated with it, and that tablet is a leader, and that leader has two followers which are also tablets.
But it's basically I mean it's your distribution vehicle.
Yeah, it's our distribution vehicle, the tablets. Okay. So yeah, I think this is just a slide which tells that, yeah, how the problem was solved, right? So Kroger, which was dealing with a multi-region system, they used a multi-region replication, which was a synchronous replication across the nodes and failover, right? In case of a node goes down, there are other regions to take it up. Paramount Plus needed multi-region plus scaling, right? So they needed a very large database which was running across the US to support their streaming needs. So that is what Paramount did. Rakuten, which is running on a Kubernetes-like system, it's not exactly Kubernetes, but it's a Kubernetes-like system, needed the native sharding of the data so that they can keep the individual data across the different nodes. Pfizer needed distributed asset transactions, or their problem was solved primarily by providing distributed asset transactions because they are into payment business and they were able to do everything. Comply advantage needed PostgreSQL compatibility because they already had this NoSQL solution, but they wanted something which was easier to manage in their applications, and that is why they went Postgres with Yugabyte and used PostgreSQL compatibility. Mindgate solutions, because of the increasing infrastructure in the UPI or increasing load in the UPI applications, they were able to use our horizontal write scalability. They were able to add as and when more nodes were coming in. Shopify, I think they were able to benefit with our distributed architecture plus data locality. There is also one interesting example, Dream11, we were talking with them before all that rule came into place and they went down. I don't know whether they went down or they slowed down. Either ways, so they were talking to us and their use case was very decent. What they wanted to do was, before the IPL game starts, they wanted to run always on 3 node, right? So their infrastructure is running on 3 node Yugabyte, and as soon as the IPL game starts, they wanted to jump to 45 nodes, right? That is the kind of load that they were seeing during the IPL games, because people were doing all this betting and everything. So they wanted to go from 3 to 45 nodes within a matter of like 20-30 minutes, and they wanted to increase to that many number of nodes, change the entire sharding logic, and support all the distributed transactions across these 45 nodes. So that was a use case we were dealing with. The company went slowed down, so I don't think the deal went anywhere, but those are the kind of applications that need more and more of distributed transactions. So yeah, this is my last slide. So YugabyteDB turns complex distributed transactions into simple PostgreSQL transactions, and that is the main selling point that Yugabyte has, and that is the reason why YugabyteDB exists. I hope.
Thank you. Thank you.
So what? There is a question, is it?
There's one more question, if Hemant can repeat it. The second question.
So the question is, if the data is multi-region, then read latencies will be impacted, right? Yeah, so it depends. So what happens is, a lot of times what we have seen is that people are doing multi-region for disaster recovery, right? So what happens is, you have data, let's say in India, EMEA, and let's say Japan region. These are the 3 regions wherein you are distributing the data. You are not distributing, like a lot of times you are not distributing the data because your users are also distributed. You are distributing the data because you think that if India region goes down for whatever reason, or if Japan region goes down because of a power or because of an earthquake or whatever happens in Japan, you want your data to still be alive, right? So one region failure should not impact your overall latencies, right? So in this case, if you have all your users in India, what the option that we can provide you is put all your leaders into the India region, right? So all the leaders will be in India region. So in normal circumstances, when you will be accessing the data, you will be accessing it from a local region, right? So the reads won't be impacted in this case, right? It is like a very standard disaster recovery deployment topology. Because what you want to do is, when you read the data, you read it locally very quickly. The day there is a disaster, you still have your data coming in, but it will be a little slow because you will be fetching it from Japan region. So yes, I think the answer to your question, whether the read latencies will be impacted or not. So the answer is yes and no. Yes, if your application is not well designed, or if you think that if your application and data distribution is not perfect, it could impact it, or in disaster scenarios cases, it can impact the overall read latencies. But generally, if the application is well defined and you are not in a disaster scenario, the latencies will be perfect.
Cool. Thanks, Hemant. I think we'll take a quick 10-minute break so that we fix the live stream. And then we'll start with the remaining workshop.
So there are,
Yeah.
there are 2 more questions for Hemant, if we can take them quickly. I'll just...
Where are they asking me questions.
On YouTube.
On YouTube.
Yeah.
I saw them there. Oh, okay.
Yeah, I have shared the questions here. You could. So there's one from Pranav, which is.
Does any write transaction always execute in one of the leader nodes in the cluster and then sent across the followers? And once the majority of nodes have written, we commit the transaction. Yes, exactly. I think whenever leaders are the primary nodes, all the reads and writes happen via the leader only for consistency, right? Any write should go to leader. Leader will be the one which will be replicating it across the nodes. In fact, also all the reads by default go to the leaders. You have different deployment topology like follower nodes that you can directly read from follower, but there is a chance that you might read stale data, right? So people generally enable them only if it is needed. But yeah, in most of the cases, all the write transactions goes to one of the leader nodes. So it's an exact representation of what Yugabyte does. Could you please explain native sharding? I'm not sure if I got the question exactly, but does it mean that the sharding in Yugabyte, maybe I will tackle that. So in Yugabyte, you have tables, and each table is divided into tablets. These tablets are physical things. Each tablet has one leader and one follower, or two followers, I'm sorry. By default, you can have more number of followers as well. But each tablet is one shard, which has got one leader and two followers. All of these three entities are physical entities, right? The followers are also not logical entities, they are physical entities because in case of disaster, you might have to go to them. So that is this thing. The data replication between these happens using raft replication, and the data is stored on this using the RocksDB infrastructure. So that is a sharding infrastructure that we have.
Cool. So we'll take a 10-minute break. Need to get. Give you one of my books. Sorry, you have my book copy? I will give you a copy of my book.
Thanks everyone for doing this, and sorry about the initial trouble. The first 5 minutes is just chaotic. Can we share Hemant's presentation with everybody? Yeah? We'll send it to you, and also I think Sandeep was trying to reach out, or Sunil had spoken to somebody regarding speaking the Rootconf database edition.
Sandeep was reaching out to me. I said that I wouldn't be able to do it, but I'll check with my.
One second, I'll check. I'll also tell you who.
Yeah, I
So
will.
Sunil from Aerospike had gotten in touch with.
Okay, cool. See.
Hey, I'm it seems we are solving a similar problem. Document. Yeah, document. So, Mongo basically document
It's very difficult. How do we monitor questions on YouTube?
Maybe I'll ask if she can share so sometime at least. Because continuously the question answer nahi
So I think we are all good now. I mean, this managing offline on okay. So all these terms that Hemant used, right? They are very common patterns that you will see in practically all distributed databases. And when I say databases, not just databases, because with database we imagine stuff like Postgres and others, but even when you see products like Kafka, Kafka has its own two-phase commit-like implementation for distributed transactions. So a lot of these things are common patterns. And one of the key challenges in understanding these common patterns is that you need to imagine a lot of things. Like when someone says that YugabyteDB implements storage using hybrid logical clocks or orders transactions using hybrid logical clocks, we don't know what that really means. I mean, you imagine, right, in your head, and maybe you get some vague idea. What we'll do today is we'll actually try to code all these things. So we'll code hybrid logical clock and see what it means. And these modules, as you can see here, they are like progressing from basic concepts about how timestamp is represented to then how that timestamp is used for versioning data in a key value storage. Then how we distribute that key value storage, that's module 3. And then the fourth module essentially is how you add transactions to that distributed storage. So we'll progress through like that. The repository has 2 branches. We are currently on the main branch, which has some code which is missing from that. And so each module, you will see that there is exercise.md, which talks about what code we need to complete to pass the test. So the idea is to make sure that all the tests pass in each module. And we'll do that by adding some missing code. And the idea is that while we add that missing code, we take time to go through the code and familiarize ourselves with the concept. So even if you don't complete the assignment, the idea is that you go through the code and understand what it does. There is a solutions branch in the same repo, which has fully complete code. So we'll start with that module 1, which says that it's about hybrid clock.
There is one question, Unmesh. Would a well-designated app requires a multi-reader write instance of a DB? When would this be preferable over a single master plus multiple?
Okay, so we'll take the questions at the end. So we'll typically be doing breaks every 40-45 minutes. So I can take the questions, all the questions later at a logical break. So as I said, we'll start with understanding what is hybrid clock and why it exists in the first place. And I have some slides to support my discussions, but those slides are not very good. So please bear with me. So you might have read, whenever you read about distributed systems, one of the big problems that's always talked about is that timestamp on multiple nodes, like timestamp on my laptop and your laptop and maybe all the servers that are running across the globe. It's impossible to guarantee that all of them show exactly the same time at obviously the microsecond or nanosecond granularity. And the reason for that, and all the challenges, it's good to keep in mind that all the challenges that are talked about, particularly in distributed system, are physical limitations. They all happen because of physics. Because the clock, what we see, it's essentially driven by a physical chip, right? And because it's a physical chip, there are always issues that can happen with any physical component. And then because of that, your clock values can go back and forth, right? And for that reason, there is typically a time synchronization service that's running on all the machines, which periodically syncs your local clock with a remote clock over the network. Now, whenever we say something happens over the network, there is another physical limit, right? And you know that nothing can travel faster than speed of light. So speed of light is a physical limit for any signal to traverse from one location to other. Add to that all the other physical issues, like because it's actually an electromagnetic signal that travels whenever your time service syncs from your laptop or any server to a global time source. When that travels over the network, there are a lot of components in between, right? There are routers, switches, actual wires and cables carrying that signal. And there can be issues with those too. So there is no guarantee, no upper bound that you can guarantee that those signals won't be delayed. And that is the reason essentially this time synchronization problem happens. And the problem is always about providing guarantee, because you might see that on your laptops which are connected to Wi-Fi. At human scale, you see that the time is always in sync, right? But at a microsecond scale, over long durations, there can always be some glitches. And when this timestamp is used to order data, like I store some data, and then later I store some different data, and after some time I see those two data records and want to figure out which was stored before other. It's very hard to do. I mean, I can, and if I assign timestamps to those, and those timestamps are not guaranteed to be in sync, it's extremely difficult to figure out which data was written ahead and which was later. So this is a very simplified view of what happens. So let's say you have these three servers, amber, blue, and green, and green is the server which is storing multiple values of this title, right? So title at 1 is before dawn, and title at 2 is after dawn, and let's say 1 and 2 are the timestamp values. Now in distributed systems, one of the big challenges what happens is that your clients might be connected to servers which are distributed across, and then those servers route your client requests to where data exists. Now, let's say this Alice client is connected to Amber, and this Bob client is connected to Blue, and they are doing this simple read operation. So the expectation is that they don't care if there are multiple versions stored on the back end. The expectation is that when I read something, I get the latest view. And that's the expectation of both of them. Now this notion of latest is very tricky, because at the most what you can do is whenever this Amber handles the read request from Alice and this Blue handles the read request from Bob, they look at their local clock and see what is the latest timestamp, and then route that request saying, okay, I think this is the latest time as of now. So give me the value latest as of Amber has timestamp as 1, so give me that. And Blue will say that, okay, according to me, the latest time is 2, so give me value as of 2. And then what will happen is Alice and Bob, and even when they are simultaneously looking at some data, one will get value of title as before dawn, and one will get that as after dawn, right? And this is like even without any replication or any other complexity that's out there. Even when data is stored on a single node, but because there is clock skew across these nodes, it's at least in this scenario not possible to provide guarantee to both Alice and Bob that they will see exactly the same data, irrespective of whatever is the latest timestamp that's on all these different servers. Now there is a caveat here. Now the issue exists because each of these servers, they are looking at their own clock for getting the timestamp, right? And this is preferred because there are some architectures where those architectures maintain a separate server, which is called as timestamp oracle. And what they do is, anytime any read request comes to any of the servers, it first goes to that timestamp oracle and checks what is the latest time. And the issue with that kind of architecture is that whichever server is acting as a timestamp oracle, like your rest of your data storage is distributed, but there will be heavy demand on that timestamp oracle kind of server, and the goal for a lot of these distributed databases like YugabyteDB or Spanner or even MongoDB, we'll see that the goal that they have is this timestamp assignment to requests, and when they store data and read data, needs to be done in a decentralized way. So they should not depend on any single server to provide timestamps. Now, one of the solutions, and you might have heard of a term called Lamport clocks. Have you heard of Lamport clock as a concept? No. So if you read any distributed system book, typically there are, they mention this clock skew problem, and the solutions mentioned are one, Lamport clock, and the other is vector clocks or version vectors. So early NoSQL databases like Cassandra and React, they implemented vector clocks, and the other is Lamport clock. So Lamport clock, the idea is very simple. The idea is that you just don't rely on system clock at all. Because only thing, when you store data and read data, if the only requirement is to know which data was written later and which was written before, you can do that even without relying on actual timestamp, system timestamp. So what Lamport clock does is that each server which is supposed to handle client request, it maintains a simple number, integer maybe like this, like 1, 2, 3, and for every request that is sent from one server to other and every response that is sent back from any server to client or any other server, it carries whatever is that whatever that number is on that server. So when a write request is sent from this client to Blue, this client maintains that logical number, say 1, and it says that I'm sending this write request at 1. This Blue maintains its own number, and the rule is that whenever you get any request and writing the data, you compare these two numbers, pick up the highest one and increment that by 1, and then you use that number to tag to the data that you are storing, and that incremented latest number you send it back. Whoever receives, like this client, when it receives this response back, it's supposed to then pick up this number, compare with the local one, and because this is now the higher number than what it has, it should set it up as its own logical number. And for any further requests, it should use that incremented value. And what this allows you to do is what is called as causal relationship. So if causal relationship means that because this write happened after this write message was received by this server, and then this second write happened after this write was completed, it's guaranteed that later writes will have higher number, because through that whole message passing chain, any later operation that happens is guaranteed to have incremented logical number. So this write will happen at 3 and this write will happen at 2. And then by looking at these two numbers, you can confidently say that because this has number 3 and this has number 2, this was written after that number 2. But there is one caveat, and you just I'm using a lot of terms, but Lamport clocks are supposed to maintain only partial order. And what I mean by partial order is, in this scenario, you can confidently say that 3 is a higher number and 2 is a lower number, and that means this was written after that 2. And you can confidently say that only because there is chain of operations that are connecting this write with this write, right? Even if they are happening on 2 different servers. But when there are independent writes happening, like this Alice is writing directly to Blue and Bob is writing to Green, there is no connection between these 2 writes. And that Lamport clock rule, actually that works only when there is chain of events, right? But here, this name is written at 1 and Green is written at 2. But just because 2 is greater than 1, you cannot say for sure that this was actually written later and that was written first. So just keep this in mind, that Lamport clock is a partial order. And the issue with Lamport clock, therefore, is that I mean, Hemant talked about globally distributed database, right? So you have, say, hundreds of nodes spread across the globe. And if you want to really look at all the data across all the nodes, and then with some confidence say which data was written ahead of other, basic Lamport clock is not enough. And that's the reason
Between
we'll...
previous slide and this is that it was the same client which was doing the two reads.
Right,
two writes.
two writes.
And in the next, there are two different clients.
Two different clients. So there is no connection between these two writes. And then because there is no connection, you cannot really reason about which happened later and which was earlier. There is another issue with this Lamport clock, and that's the reason this Lamport clock is not directly used for data storage. One obviously is partial order, but other is that there is no direct relation with actual timestamp. And in databases, whenever we store any data, it's good to have some connection with the real timestamp. Like this write happened on Saturday, such and such time, right? That kind of, because when users query data on databases, they will like to know, give me the report as of version that existed on last Saturday, 6 p.m. And if we just use these logical numbers, 1, 2, 3, 4, it's very hard to relate to real time. And that is the reason you will see that in all the real databases like Yugabyte and others, even Mongo, all the open source databases, and we'll talk briefly about why open source databases support this or use hybrid clock and why cloud services they use something else. But the trick they use is to combine the system time along with this simple integer like Lamport clock to make sure that you achieve same behavior as of Lamport clock, that any related events like these, you will be able to tell from timestamp which happened later and which happened first. But you also have the values that you have or values that you assign as these numbers. They are actual timestamps. So if you convert that long into a real timestamp, you will see Saturday 6 p.m. Kind of thing.
Sorry, one question.
Yeah.
User-facing time semantics, you said.
Right.
Can you give an example of that? So, I mean, I'm just trying to visualize it. So,
No, user-facing is.
Like, so would a query be like
select star from such and such as of time, right? As of 8/9/2002, 6 p.m.
Right. Okay. But
With
that's not the only case, right? I mean, like user-facing time semantics, are we talking about user-facing time semantics where that time is explicit? Like, for example, a modified date column or a created date column. So that's clear that it's
right. It's that.
But is it something more than that as
well? Okay, let's say it is that for now. For now. I don't know. Is this visible? Is this big enough? Right. So if you look at hybrid clock, which is extension of this concept of Lamport clock, and we can look at the code as well. So if you look at this code, there is this component called as hybrid clock, and what this does is it interacts with your system clock. So this clock object that you see in here, it's really a system clock, which is abstracted so that for your tests you can use stub clock. But when you use system clock, it's just using this. And in any programming language, I mean, you have an API like this. So your hybrid clock and each server process will have an instance of this hybrid clock. So instead of directly calling get me time of the day, like system.get current time millis or get time of the day, you will maintain instance of this hybrid clock, and it will talk to this system clock and manage something called as what is the latest hybrid timestamp that I need to assign, or I need to give whenever someone asks me the latest time. And this hybrid timestamp, you can see that it has two components. So it has the actual wall clock time that you get from your system timestamp, and then there is an integer which you kind of which is managed very similar to what we saw in case of Lamport clock. So what we'll be doing as an assignment is we'll implement this now method in hybrid clock, and the idea is that you take your time. I mean, just to go through the code. There is a solutions branch which has the solution, but we'll walk through how the now method is supposed to work. So the now method essentially gives you now this kind of a tuple or a pair, and that pair is that hybrid timestamp instance. And very similar to how we passed that logical counter across all messages, we pass this entire pair. Like we pass timestamp as always a pair. When any server receives this timestamp, it uses hybrid clock to get the latest pair of system time and ticks, and then it applies some logic which is in the code as well to pick up the latest one. So that picking up the latest and incrementing, that logic happens over this entire pair. So the idea is that you, in the end, you get the same semantics as Lamport clock, saying that even if you have clock skew, so you have this number as say 900 and that was 1000. So this clock was lagging behind. The idea is that you use this counter in such a way that after this message is received, the timestamp value should be higher than that 1000. So what I think instead of me explaining this, what you can do now is we'll try to make that test pass by implementing hybrid clock.now method. And then we'll discuss whenever you get any issues. So there are tests. There is this hybrid clock test. Just take some time to go through that to see what that's doing. And the idea is to pass this test, which is currently failing. On the hybrid clock class, I have always also mentioned the links of real source code for 3 databases that I went through. But one of the hope from this code base and this workshop that I also have is we get some confidence in going through the source code of all these open source products. So we'll take like 15 minutes for you to go through the code and just familiarize. In case you want to refer to the solutions branch, you can refer to that as well. And
Snacks is here, but if you want, we can do 10 minutes.
Snacks is here.
But that's okay, we can wait for 10 minutes.
Everyone is in the middle of
Yeah, let's finish.
So the first test, essentially what it's saying is you call system.getTime or that internal clock.now, and you see that the time is unchanged. That can very well happen between 2 system.current is call. And if that happens, you need to have that integer counter that we have associated with timestamp. That should be implemented. So we can just focus on the first test right now to make it pass. The other two tests are about when you have a hybrid timestamp and you receive another timestamp, how you pick and merge those. So the first test is about just when you call that hybrid clock.now, how to make sure that you always get a monotonically increasing timestamp. And the other two tests are about when you receive a timestamp from someone else and you need to make sure you merge that with your local timestamp, what logic needs to be there. And that tick logic is probably we'll just demo and walk through. But that first method we'll write. So do ask me questions if you have any, because there are a lot of clocks and timestamps and stuff out there. But essentially what we are doing is, so this clock you can consider as a system clock, and we are just wrapping that. So none of the processes get direct access to that system clock. It's always through this wrapper that we have. So essentially, whenever someone asks for a timestamp, we always give this hybrid timestamp object, and not a raw timestamp that you get from your system libraries. Done, right? You got the, yeah.
In a single machine, with that millisecond precision, we have a order in the events, right?
Yeah. I mean, microsecond.
Yeah, microsecond. Okay, so across systems.
So what this is guarding against essentially is if your two consecutive clock dot now gives you same value, same or lesser value. Like your time can even go back in time, timestamp value. So you are guarding against that consecutive calls to this now method will always give you a monotonically increasing timestamp, even when your system time is behaving badly.
There are two questions. This is more about. This is another question. So someone can see if it exists to take tags on this
Yeah, tick systems. Yeah, so the comment is right from Stardust Nick. So ticks exist to for the tiebreaker. So are we done with the now implementation? I mean, it should look something like this. And you can look at the solutions branch, but I think it is like that. It's essentially guarding against two consecutive clock.now calls, either going back in time or remaining the same. So you are guarding against that. The other two tests, uh, are essentially about how you merge two hybrid timestamp values. And let's say this is the hybrid timestamp value on your process or your machine, and then you get another timestamp from a message, as we saw in the example. Then you need to have a logic to merge those. And simplistically, the logic is, and we can go through the tick method, is essentially to pick the largest wall clock times of both the timestamps. So it has two components, wall clock time and ticks. And then merge the ticks. So essentially, you get, when you merge these two hybrid timestamps, the idea is that the result should be higher than any of those. And it should happen like that irrespective of whether the received timestamp is higher or the timestamp you are comparing against is higher. So idea is that you get a monotonically increasing number. So you are guarding against your system timestamp going back and forth or remaining the same, and also making sure that when you merge two timestamps, you always get a higher number. Can you think of any other test that can be added?
Sorry, before we go to the next test, did you switch to the solution?
Sorry. Yeah. So it's just guarding against clock.now. And so that clock.now is really your system time.
It takes plus is something.
Yeah. I mean, it just increments the ticks. So if the timestamp is the same, then the tick is the thing that increments. So if you always get the same timestamp or the timestamp values as lower, you increment the logical counter. And essentially it breaks the ties.
Yeah, so I missed this. I was just writing and testing this. So I basically implemented, because like treating this as now as a software problem, right? So like there are some interfaces, there are some implementations, private method implementations. So I implemented this as simply return tick this dot latest time. How would that return tick this dot latest time?
Okay. Yeah.
I mean, again, it's just
that
purely treating as a and I was
So you are merging the latest time with now.
Because
should
that's
work the
what,
same.
I mean, that's what I made
Should
of.
work the same.
And again, I haven't seen this before, right? So,
That's absolutely
I mean, what I infer of this behavior, tick is of course public, and then it calls these class private methods. So it seems that it is doing the same thing, because the
It is doing the same.
the requirement. what the test specifies that you need to preserve monotonicity.
Monotonicity,
Right?
yes.
Then
yes.
that's
So
what
it's the
it is
same. So
doing.
tick is essentially merging.
Correct. And tick is your
merging to it.
counter.
Tick is your
Tick,
counter. Yeah.
tick. So then
So this is actually better. Yeah.
so then because so when you showed this, the only thing that I haven't checked yet is if the existing implementation of tick accounts for line number 40.
Yeah, it will because
But
it's essentially
I
picks
would
up
expect-
the
yeah.
highest. And,
Yeah, correct.
yes.
And well, that got the test to pass, so I was like, okay.
Yeah. So that's actually logically correct thing to do because essentially what tick is doing is merging.
Yeah, I
Two
mean,
timestamps.
it's merging two
And
timestamps.
that's exactly what you need to do with your
Correct.
own system time.
Because
It's just
tick is actually doing line
yes.
41 plus
Yes.
the merge part.
Yes. Yeah, actually this actually this code is not handling other case where your clock time is higher than latest time.
Right.
So it's not handling that other branch.
Correct. So
Which
my,
is
my interpretation of that tick
yes.
actually handles handles all possible cases
All the
of
possible cases.
ordering of
So there is no test that tests the other path because for now
yeah.
we should have added that test because we just have one branch, right? That this current clock time is less than or equal to latest, but we are not handling the other part that should be handled. And this tick method, you can see is that it's handling all the possible branches because you need to test both conditions, right? If this is less than the latest or latest is less than the current. Do the merge properly, yeah. So as you said, I mean this is. Yeah, you can actually implement it like this. And that will take care of all the possible merges that need to happen.
Yeah, because that is already written. That was not written, then you would have to.
Yes, because that tick is already written. Yeah. Cool. So any questions on this? I mean, this is the basic hybrid clock implementation, and you can take your time later to traverse through this GitHub links for CockroachDB and MongoDB and YugabyteDB.
So the tick is an integer, right? So what happens when the integer rolls over?
Yeah, that's a good question.
To the max and rolls over to 0 again.
I mean, so the thing is that when your wall clock actually progresses, you reset that tick to 0 because your value is a composite of wall clock and that tick. So it's never that only tick increments indefinitely. And I think that merge implementation of tick rate, I think it handles that case. Yeah, so it handles the case where you reset that tick part. Cool. So I think there are snacks getting served, so we can take a 15-minute break for snacks. And when we come back, what we'll do is now this is just a clock and timestamp, but we'll see how these timestamp values are used along with the storage. So when you store a row in a table or a key and a value, how these timestamps are used. And that module 2 is about that. So we'll take a 15-minute break for quick snacks. So you keep calling now, it will always first refer to your...
clock is stuck. Every time you are saying same
your-
value. Just
Your
one
clock
given
is stuck,
value.
your
Yes.
system clock
Yes,
is stuck.
Yes, yes.
Yeah, then it's an issue.
Yeah.
Then it's an issue. I haven't seen system.
What was it?
He's saying your system clock is stuck indefinitely.
Okay.
Your server system timestamp is indefinitely stuck to the same value, frozen to some value.
Right.
Then you're only relying on that tick.
Right. Then you are on.
Yeah, but I think before that integer tick overflows, you will have your system infra fixed.
Yeah, usually clocks are crystal based, right? So
Yeah.
they may go out of sync, but
Yeah,
stuck is the case
yeah,
where
and that
crystal
will
is
happen
failed.
before that integer overflows. Right?
So how
Yeah,
this
you'll have enough time to fix.
how this requesting or clock is being used in actual system? Why? Because let's say we are taking this value as an integer, okay, we can take it long, but will there be a possibility in real or practical scenario that integer value will overflow?
No,
using
so-
that equal timestamp.
I mean, it won't, right? I mean, if your wall clock time progresses,
Yeah, it is progressing, right? So
yeah,
we are
then you
resetting the value.
reset that tick to zero.
Depends how we are using it. So that was my question. Let's say it is very high TPS and we are calling and getting.
So like
so
within
at
a microsecond, you are getting like
Yeah. So,
million requests.
Yeah. So
Uh,
does this happen actually? Very high
I mean, not million requests, but yeah, I mean that tick will take care of if you get a lot of requests within a microsecond window, but not so many that it overflows.
There is a question, I think. We were talking about the another branch thing which is missing in the test cases. Can you explain the other branch thing missing in test case?
Yeah, right. I mean, if you, there is a question about why we used, why we call tick from the, in the now method, because that it handles all the cases of how the two timestamps need to be merged. What I initially coded was just like one branch. Your latest time is higher than what your system clock gives you. But there is other case as well that your latest time is lower than what clock gives you, and that needs to be handled as well. So that was the other branch. So we are taking a 15-minute break now. Okay, we'll get started with the next module that we have, and which is called as version KV. So what we'll see in here is, let's say you have this hybrid timestamp that you now want to use to version data whenever you store that data. We'll see how that can be achieved. We'll walk through the code, and again, there are some snippets that we need to complete. So the way we will do that, and I think, yeah, just before we proceed, there was a question on YouTube stream about some data loss and some scenario, but I think we'll park that for now, because it will be good for whoever asked the question to maybe try to implement that scenario in the unit test, because then it will make it clear. Right. So we looked at basic hybrid clock mechanism, as I said, and now we need to see how that's used for actually storing the data. The way we'll do that is in two ways. One is if you have to just store that in memory, like an in-memory hash map. And the other is how typically used in all the databases, where you use a storage engine like RocksDB for your data storage. And practically all modern databases, you will see that they use either RocksDB or a similar storage engine of their own, which is implementing storage mechanics like LSM trees for storing that data. So if you see in this module, there is a basic interface called MVCC store, and MVCC is a short form for Multi-Version Concurrency Control. We won't be doing any of the concurrency control part in here, but this will store only multiple versions of same data using hybrid timestamp that we saw in the first module. And one thing obviously you see in here is it has like put and get methods like you typically expect in any key value store. But the key you see here is a multi MVCC key. So if you are storing, let's say, account and balance, or customer and status, or customer object, or any of that, you will have some logical key for your data that you decide. And that key will always be associated internally when you store that data. It will always be associated with this hybrid timestamp. So whenever we store data in the storage, it will always be stored with this MVCC key. The other methods that you see in there, and obviously what you expect from a version storage, is ability to read up to a certain version, right? You get snapshot as of a particular timestamp. You get all the versions, like the history of all the versions from a particular timestamp, and these are the typical methods that you expect. And then there is a helper method which says get me the latest. So I don't pass the explicit MVCC key or timestamp, but get me the latest.
Sorry, what is put batch? Did you talk about that?
We'll talk about that a bit later, but typically that put batch is used if you now relate this to your SQL layer, SQL layer works on a table-like abstraction, right? And table has a row, and that row has multiple columns. So when we insert a record from SQL point of view, we are actually inserting multiple columns, right? Each having let's say a different key. Now, how you store a row in at your storage level, there can be multiple doing that. One is just serialize the entire row as a blob, like a byte array, and then store that as a single value in this key value store. So your key is your primary key for the row, and the value is the entire row serialized as a byte array. Or what you can do is you can construct a key for each column and then store each column as a separate key value. Right, so we'll see how that can be done, but that's a like you construct a key for a column saying you table name, primary key, column name. That's the key for your column, and append the timestamp that creates the MVCC key for each column, and then you store each column as a separate key value. But if you need to store each column as a separate key value, the semantics at insert level, where when you insert a single row, that right at the storage level should be atomic, meaning it should never happen that few columns are stored and few columns are not in the case of a failure. And if you need to do something like that, that put batch kind of a method is useful. And RocksDB provides that.
What you said makes sense, because I was always thinking that what you said, right? Like, so row, for example, in database is like, e.g. it is a tuple. So it is always one row. But if you take a RocksDB approach, then then each of these are decoupled, but they have to be held together by something which is one layer above the storage layer.
Right, and particularly for multi-version storage, right? Whenever you update a row from SQL database point of view, it can very well happen that you update only few columns. If you every time serialize a row and store each version as a separate row object, you are unnecessarily incurring the cost of So storing each column separately, it helps in optimizing that bit. So we'll look at this in-memory MVCC store, and you can see that this is a simple concurrent skip list map. And the reason a skip list is used in here, I mean this is for a demo purpose, obviously, is that the interface of this skip list, the way the data is stored in skip list, and the way you can traverse sorted data, like going from a key to all the previous keys and stuff like that. This interface is very similar to a storage library or storage engine like RocksDB, because RocksDB internally has, if you see the data structure that's used in the LSM tree, it's similar to the skip list. It is a skip list for meme table for a lot of it. So this is just for the demonstration purpose to see how your in-memory implementation of this MVCC store can be done. But the key aspect there is uh, that this MVCC key, whenever we store multiple versions of data in any storage, we need to have some way to order that data properly from storage engine point of view. So when you store um, say a key with some timestamp and then store it again with another timestamp and store it again with another timestamp, it needs to be ordered at data structure level. Because only then, if it's ordered properly at the data structure level or the storage level, it's only then that we can traverse it in any meaningful way. Because otherwise, it will be very difficult to traverse it when we say that traverse from this version to this version. So all the versions, they need to be packed together and ordered in meaningful way, right? And the way we order that, I mean, in case of Java, you essentially implement a comparable interface, which allows you to compare two values. And any data structure that stores then these keys, it orders these keys with this compare logic. What we'll do now is try to implement this compare to method for MVCC key. And what we need to make sure is that it needs to use both of these things, right? Obviously, the logical key that we have for our data as well as timestamp, they both need to be considered when we order the data. So our assignment is to implement compare and make sure that the corresponding test passes. There is a MVCC key test that needs to pass. And there is an important point here, maybe I'll just talk about that, is that when something is a byte array, there is no equals on a byte array, right? I mean, you have to compare it byte by byte. And when you compare a byte array data, it's called as mem comparable. So the values that each byte has essentially decide how the data is ordered. So whatever your data type for the key is, when you store that as a byte array, and you expect that to be used in expect that to be sorted at the storage level, that conversion or encoding from that data type to byte array needs to make sure that byte array is order preserving. So if your data type is integer, for example, and you have values 1, 2, 3, 4, you know that 4 is greater than 1. But when you represent that in a byte array, you have to make sure that that order is preserved. And it is called as order preserving encoding, and which becomes more critical as we'll see when we use a storage like RocksDB. Because RocksDB or any other lower level storage doesn't know anything about objects like MVCC, right? They will only know about bytes. And so whenever we convert any higher level logical object into a storage level encoded byte key, that encoding needs to be byte order preserving. So here we have to just take care of order preserving and encoding for that key part. but we'll see that when we look at the RocksDB storage, and there is a RocksDB storage in there. We need to take care of encoding the entire MVCC. So it takes some time to go through the code and implement the compare method. And also, if you have any questions about the other, so there is this test that we'll go through as well. This in-memory MVCC store test. So any questions anyone has? Compare implemented. We can go through that. I mean, it's so the tricky bit is how you compare byte arrays. So you need to use this compare unsigned utility method so that you compare it properly, and then you compare the hybrid timestamps if those byte arrays are same. And if you've gone through these tests, there are some utility methods like is visible at, which we'll see how they are used once we look at the storage implementation. So when we are storing at multiple timestamps, is this key visible at a particular timestamp? And we just essentially compare that with the timestamp value. And then there is this other utility method saying, trying to figure out if the key starts with a particular prefix. Again, as I said, when we store multiple columns as separate key values, that becomes easier. So we'll take say a few minutes to go through this in-memory implementation tests. And what we are doing there is essentially storing multiple versions of same key at separate at different timestamps, and then trying to read either the latest value or value as of a particular timestamp. So the first is just simple getting the latest value. So we store 3 versions. You can see at 3 timestamps. And because you have stubbed the clock, essentially it's simple integer values that we are assigning. But these are 3 versions of same account 1 key stored in a in-memory store. And you can imagine that they are ordered as like timestamp 1000 version comes first, and then 1500, and then 2000. And latest, if you see the implementation, yeah, it's getting the floor entry for the search key. Now this is another a bit tricky thing, because what can always happen is that when we are storing versions like these, the as of version you read might be a very different value, right? So while storing your timestamps were like 1000, 1500 to 2000, but while reading, it can happen that you read at timestamp 500 or read at 4000, right? Or read at say 1700. And then you need to read the latest value that is visible at that timestamp. So if you read at say 1200, it should return the first value, first version, and not the rest of the versions. So versioned reading, when we do, it's important to implement it in such a way that your fetch won't always be exact match for the version key, right? Because that version, because it's a timestamp, it can have any value. So the second test is essentially testing that you fetch as of value, as of a particular timestamp, and as of as I said, it's a floor entry. So floor entry is highest value lower than the given value, right? There is another tricky thing that we need to worry about, is that when we use things like this floor map and ceiling map, and when we expect the keys to be ordered, the key storage is across multiple keys, right? So when you sort keys, it's across multiple keys. So here you can see that there is key 1 and key 2. So essentially account 1, account 2, account 3, account 4, like in real database will be different keys, right? And when you scan this kind of a storage space based on some ordering mechanics, you have to make sure that as you traverse the keys and values, you need to stop when the key boundary is reached, because otherwise you will just fall through and get different keys when they are not expected, right? So when you are reading key 1, it should not return a key 2 value, even when they are sorted right next to each other. And that needs to be explicitly coded, because when you just traverse an iterator, otherwise you will fall through the different keys. And then there is this last test, and we'll talk about that a little later. But when you have, as I said, multiple columns stored as separate key values, and then you need to read entire row. So here, can you figure out what the row is? So essentially, let's say it's like a customer kind of a table, which has name and address, just 2 columns, right? And you can see that when updates were done, there are 3 versions, 3 updates done to address, right? So that customer 1 address there are 3 timestamped versions for that. And when you store stuff like this, you should be able to read one entire logical row, right, at a given timestamp. So can you take some time to figure out how that scan prefix of is implemented? Maybe go through that and try to explain to me. I mean, this is still all in-memory storage. And next what we'll look at is the ROX3B storage, which is very close to how real databases implement stuff. So why are we asserting on just like 2? Because we see that there are multiple versions, but you always expect, so that row has only 2 columns, right? Name and address. So the implementation should always be that you should always get a single row which is 2 columns. Just the values of those columns you need to be properly fetching based on the timestamp at which you read.
Question. Unmesh. Can you sum up quickly?
Yeah. So there we are using this tail map method. Is that the right thing to do? Yeah, that order preserving codec we'll see more when we look at the ROX3B storage. So that tail map thing, essentially we are doing like from the minimum version of that particular prefix. But important thing to note is that when we give prefix, we don't explicitly have the key, right? We don't know the key that we are reading. We are just reading the prefix. So in that ordered storage, you need to point to the first key with that prefix. And the first key will always be minimum version. I mean, anything higher than the minimum possible version. So the way that tail map is implemented, and we'll see the like RocksDB equivalent, which is iterator seek. Even when you don't specify explicit key, you're just providing the part of the key, right? The way it's implemented and the way it's sorted, it will point to the first key with that prefix. And that's very useful when you are storing columns like that. So there are three things we are doing here, and we'll just quickly go through that. One is, as we said, we are scanning by prefix, and we go to the first key with that prefix. The other thing we are doing is that we expect multiple versions for each key, and so we pick up the keys which are lower than the as of time. And here I think we are just overwriting that result for the logical key. And logical key is the part which is key without the timestamp. Right? That's the column name in this particular test. And the third important thing we are doing is we stop traversing when we reach a point where that key doesn't have the same prefix, because all the keys are ordered. We don't know the boundary, right? I mean, the storage doesn't know the boundary. It's just sorts all the keys just like that. So very similar to what we saw in that in-memory map. RocksDB, you can see you can work in the same way or use the same way functionally. At implementation level, there are a few nuances. The first and foremost is that RocksDB won't understand an object, Java object like MVCC key. Right? So that compared to method that we had, it's not very useful for RocksDB. For some time now, actually RocksDB allows you to register a comparator, which then you can use to control how RocksDB stores and orders your keys. But you will see that most databases won't use that, because for every key insertion and scanning, if you need to go to that comparator invocation, it slows down the traverser. Particularly so when you are doing a cross language boundary thing, like this is Java implementation and RocksDB is a C implementation. So there is a JNI layer in between, and you don't want every time you insert something for that JNI level to cross. So, because RocksDB doesn't understand anything like Java object in the CCK, you need to encode that into byte array. And whenever your database uses RocksDB as a storage, any rows, tables, etc. that you store in this RocksDB, essentially they need to be encoded into byte array. And as we said, because we expect, and RocksDB does store all the key values in a sorted order, we need to make sure that if we expect certain logical order in our keys, like when we append with timestamps, they need to be sorted in a specific order. The encoding that we do for that key needs to be order preserving. And if you look at, I mean, I was actually thinking of giving this as an assignment, but I think it will take a lot of time unless we use ChatGPT. But I think we'll walk through this encoding. So the way this is encoded, and encoding is essentially you convert a logical object into a byte array. You can see that our logical key, like account balance that we were storing, that was already a byte array that we serialized. The next part that we need to serialize is hybrid timestamp, right? And hybrid timestamp has two components to it. There is a wall clock time, which is a long, and then there are ticks, which are integers. So essentially, we need to store a long and then appended by an integer, and that like a contiguous byte array into byte array, in such a way that they are ordered properly. So a timestamp of 1 should precede timestamp of 2, and it should precede timestamp of 3, etc. What you see here is the values are inverted while they are stored, and we'll talk about that a little later. But what this inversion does is that instead of storing those keys in a ascending sorted order, like storing 1, then 2, then 3, it will store them in reverse order. It will store 3 first, and then 2, and then 1. And the reason this is done is that RocksDB, like storages, they only have an iterator which supports seeking to a particular key and then traversing forward from that key. So you seek to, let's say, a timestamp of 2, and then the natural operation that you do from that point is you traverse, you go to next, you go to next, you go to next, right? But when we are traversing history or historical versions, like we typically do in version storages, you need to traverse backward from a particular as of time, right? So you say, I have version 1, 2, 3, and I want version as of 2, or all the versions as of 2. The way you need to traverse, and that's why we had that tail map thing that was done there, right? So you go to version 2, and then you go back to version 1. So this is like reverse iterating, which is not very natural in RocksDB iterator or any iterator that typically you seek and go next, and that's the reason they are inverted. I'm just highlighting that because these are some of the nuances when RocksDB like storages are used for version storage. If you look at RocksDB MVCC store, it has very similar tests to our in-memory store. So take say 5 minutes to just go through these RocksDB tests. And we'll discuss if you have any questions. And if you like, you can tweak and add more tests as well in there. In fact, all the tests from that in-memory MVCC store test, right? I mean, if you just replace this MVCC store instance with RocksDB MVCC store, they should all pass. So if you replace one of the tests in that in-memory test suite with RocksDB store, I think that need for order preserving encoding becomes a little more clear, because there we had tests with like multiple versions and the expectation that they are sorted in a particular order. And when we store these MVCC keys in RocksDB store, we essentially encode those keys in byte array, as I said. Any questions on this RocksDB stuff?
Just one question. So when we are storing a byte buffer, right? In byte buffer, the keys and values.
A byte buffer is just a contiguous byte array.
Right, right. So there we are not storing length of key because we have null set.
You're not stating length of logical key. Yeah.
Ah.
I mean, you need either a prefix with a size,
Correct.
or you need to have a separator. And the other thing is that the remaining part ahead of that, after that separator is fixed width. So you always know that you're like one long followed by one int. It's 8 plus 4 bytes, 12 bytes. So you can always, what you can do is when you read back, you know that you go to the end, from end 13th byte will be that separator, and from that everything is your logical key.
So around RocksDB, I mean, I don't have a question, but it's an observation. I'll try to frame it because still somewhat fluid. So RocksDB is, I mean, with RocksDB we are having to we are having to be aware of the physical storage layer, right? I mean, because like I mean, what's that implementation? When we say the
encoding, is it?
Yeah,
The order.
encoding, right?
Yeah, I mean, you need to be aware of, or you need to do that mapping from your logical logical keys to your byte array, physical storage.
That's why I'm
yes,
saying
yes.
it's like physical layout of bytes.
Physical layout of bytes. Yeah, I mean, because RocksDB is LSM tree, and it relies on
that's
sorted
right.
order of keys.
Okay. So is there a is that common, somewhat common in the world of databases, or in the world of databases that use LSM trees?
Yeah, because LSM trees will always depend on, I mean, will always be sorting, keeping keys in your sorted order. And that works very well, by the way, with version storage, because you need your keys sorted in a logical order.
Query is a sorted query saying give me versions less than or as of.
Right. Only thing is that when it goes to storage level like rocks, they are opaque bytes, and only comparison that happens is
correct. So the
raw byte level comparison.
The MVCC store, what we're calling it, the RocksDB MVCC store, has to be aware of
that aspect.
Physical storage bytes.
Yes.
Or
because that's like a contract that your upper layer has, that I need a particular sorted order.
Right.
Of keys.
So I suppose that makes it
efficient. I mean, that makes it efficient.
So that makes it very efficient.
Yes.
That also introduces coupling. So it would be. I mean, I again, maybe this question is academic. That it makes it extremely difficult to then replace RocksDB with something else, because not only is a physical, because now at the RocksDB you have.
You replace it only inside that MVCC.
I mean, it's encapsulated.
Kind of.
Encapsulated within that.
And you see that, I mean, databases like CockroachDB, for example, they now have their own Pebble storage.
I mean, because
which is a complete
those things are not extremely uncommon, right?
It's common to
swap out storage layer with another storage layer,
Yes.
because maybe like what Hemant was talking about, some new use case comes about, you need to support a customer use case that may not work best with a particular storage.
Yes. I mean, even Yugabyte, for example, they have their own kind of version of rocks. Fork of rocks. I mean, they call it RocksDB. But yeah, I mean, and for that you will have a layer like MVCC store, like what we had.
Yeah, so you
encapsulate that so that rocks is not leaked to layers above.
There is another question around the This one. Dots.
Does not. Yeah, I mean, app needs to make sure that keys are encoded for natural ordering, or else you provide your comparator, because Rocks also allows you to provide your own comparator. There is one more thing that we'll look at before we break. Probably is there is yeah, sorry.
There is a method called collect visible prefix record as well.
Right.
Can you help me?
And that's used for prefix scan, right? Yeah, I mean, what we are doing in prefix scan is, I mean, maybe we can go through this particular test, right? That is using prefix scan. So what we expect is we seek to the first key which has customers_customer1 prefix, and then we traverse ahead, scanning through all the versions. But if we are reading at a particular timestamp, like T2, then we have to make sure that we don't get T3. And that's what that method is doing. Essentially, it's scanning through, it's sticking to a particular point, scanning ahead, and filtering the keys that are not visible.
In this case, if at line number 114, instead of T2, I give another wall clock value like 2100. So line number 114.
Right. So if you give a different time, yeah, you will get. So there are three possible values you get for address, right? One that's if you give 1400, what you should get is that first old address. Yeah. Yeah. Essentially, that's what that method is doing, and also making sure that it stops when it crosses the key boundary. I mean, crosses the prefix, because so you can imagine that this is your one row and multiple versions. When you go to customer 2, this is your one row, this is your start of second row. It should stop iterating at that. Yeah.
I noticed that as a private method, so I didn't maybe.
Which one?
The same method.
Oh, the same.
Collect visible prefix records.
Right.
So there at line 140, is there a branch missing? Because it says if not results dot contains key, then results should good. But if we want to collect versions, right? So shouldn't we have a case which says if the key is already present, 141? No, you already crossed it.
Yeah. No, I know. So yeah, okay. So what it's doing there is essentially picking up only one version.
Okay.
So if we want all versions, we need to extend that method, or have a separate method. Get like all versions.
Yeah,
where you traverse differently.
At least English language, like it said prefix records as of, so which means expected to return and also what we saw.
Yeah, I was thinking. So basically,
okay, that's what
next over there it says size of
2000.
Okay. Yeah.
Values dot size of equals 2, right? So then we will have to collect like
all
like
the versions.
old address, mid address. So we'll have to. So it seems like if we don't have that.
Okay. Yeah. So sorry. Yeah. I mean that name is little misleading because that method. I mean when I wrote that, essentially that was for the table implementation. Okay. You get all columns with prefix at a particular version.
Okay.
So per column you get only one value. That was the semantics I had in mind. If you need to read all history, then yeah, I mean then you need to code that. I mean you remove that check.
Yeah, I mean, or you will have to do result.get and then
Yes. Yes.
like basically add.
Yeah.
Logical add. So I think, I mean, the way it reads right now, if we were to pick up that in memory MVCC store test
Right.
and run the test can prefix as of returns visible version per logical key.
Yeah.
That might fail the values.size. It seems to me.
Okay, you can try that out. Yeah, I know it should pass because I thought I coded that. So it will give you like one value per logical. So I mean you can always change that to RocksDB.
Right. Yeah, I know there's a change.
Yeah, but I mean I see it's confusing.
Yeah,
the
it's
way
just confusing.
Maybe I should just add a comment there that if you need to read all history with all versions
To that value.
up to that value. Yeah.
Right. So behavior is correct.
Yeah.
Naming
is
maybe-
confusing.
maybe-
Yeah, I agree. So just to demonstrate how a table then is stored with this kind of a MVCC store, there is a example implementation of a table there. You can see. I mean it's very similar to the test that we saw, but adding a little more sugar on top, mapping it to a row and column. So like it's easier to map to insert or update row. Like
What does this test mean? What is a table? Because I think
so table is just adding a wrapper around RocksDB store, introducing the concept of a row and column. So essentially what you do there is instead of inserting individual key values,
this is essentially doing insert into table values.
insert into table values. Yes. I mean just to map, add a layer in between RocksDB and SQL. And that insert row is essentially doing the same thing internally. I mean constructing a key per column, and that's where it is using that put batch method, because the expectation is that entire row content should be atomically stored at the storage level. So this is just to map it a little, to make it a little easier to map to SQL. Because Hemant talked about Yugabyte, Cockroach, and all others, they are SQL databases. But essentially their storage there looks exactly like this. So if you open Yugabyte or Cockroach database, their storage level will be layer will be exactly the same. And interestingly, your Mongo and other NoSQL database storage layer, it will also look very similar. So at the storage level, there is less difference between a SQL and a NoSQL database.
Any DB which is in RocksDB as storage will have this.
And using MVCC, we'll have this kind of a yes. So as I said, Mongo uses hybrid timestamp. Mongo, Yugabyte, Cockroach, even Cassandra. I mean, Cassandra doesn't do version storage, but storage layer is very similar. LSM trees.
Cassandra has column families, so
Yes. Right. Um, so yeah, I mean that's a good point. So here we looked at like one table mapping to a RocksDB instance. But you can, I mean how you map that logical logical group of data, like a table, to the physical storage varies. When you say column families, you group a single row, you create multiple groups for a single row, and you group columns together. And for each column, you can have a RocksDB instance. For each table, you can have a RocksDB instance, or you can have a single RocksDB instance shared across multiple tables. I mean, what we have here is, because we are prefixing with table ID, essentially this is like multiple tables packed in a single RocksDB instance.
That will avoid too many files problem as well, right? On a disk.
I mean, if you have too many RocksDB, yes, too many tables.
Too many tables. Separate instances.
I mean, too many small tables. Yeah. So the next thing is we need to take a break. Is it lunch? Lunch.
Ready.
Lunch is ready.
Okay. So we can take a lunch break. But the next thing now we need to do is, we looked at single storage right now. When we do distributed storage, essentially you expect multiple such RocksDB instances spread across replicas. So we'll look at how that's done after the lunch, and then it becomes a little tricky to make sure that when you insert in multiple RocksDB instances spread across replicas, how to make sure that insertions and updates are done atomically. And that's where this transaction bit comes in. So those are the next two modules. So we break for lunch. So we'll break for lunch and be back in like 45 minutes.
Yeah, that should be good. 15.
share. So what we'll do is now we'll see this basic storage that we have, like a key value version storage with hybrid timestamp. When we now need to create a cluster where we have multiple nodes, each individually having this kind of a storage, and then a client interacting with it, how that works. So before we go there, so we'll be using a small toy framework that I have, which I use for experimenting with distributed systems, called Ticloom. So I will just walk you through. So there is this hello world example of this Ticloom usage. Now what it allows you to do is to have your own implementation, and with that implementation then you can create a cluster. So if you need, let's say, a cluster of 3 nodes, it will create 3 objects of this implementation, and then it has all the utilities for these various nodes to talk to each other over the network, or clients to send messages and receive responses from these networks. So if you take few minutes to go through this, so each of the processes, client as well as server processes, they are essentially identified by ID, a unique ID that you can refer to in your tests. And then there is a cluster utility which essentially allows you to create multiple instances of these process objects to form a cluster. And this framework has facility to simulate network and storage. So we'll mostly be using simulated network. So if you remove this, right, by default, all the storage replica objects, they will talk to each other over network. But then they will, if you don't use simulated network, they will use actual TCP/IP communication. So we'll use simulated network. So what we, while implementing a distributed system, are expected to write is the server side implementation and the client side implementation. Now each of these implementations, they need to do just obvious 2-3 things. Like any process, they need to declare what kind of messages or requests they expect, and then the handler for that. And then within that handler, they need to really deserialize the request that's sent to them, act on that request, and then send the response back. And it will be sent to the sender. So if the client is sending you the request, it will send it back to the client. And then there is a client that you are expected to write, which essentially just provides an API for you to talk to these server-side processes. So this simple hello world example, it just has a client with single method saying say hello, and then which sends a hello request to the recipient server. And client as well has a handler, obviously, for the response message. So the communication is all asynchronous. There is we don't block. So we don't call a method and then expect that it will block to get the response. And that asynchronous communication is modeled by that future object. So if you are aware of future, it's an object for async, for communication across async boundaries, right? So you get a future back and then you wait for the response to arrive. There is another utility method that essentially waits until certain condition is fulfilled. Now in this case, it waits till that future is completed. But what it does internally, and I won't go in much detail of the framework, but just to it actually tells each of the objects that we are building, like the server-side components as well as client-side components, to make a progress in steps. So what it allows you to do, and that we'll see in some of the later tests, is you can execute the entire cluster to a point where only few messages are passed from one node to other. You halt there, you assert on what's the state of the cluster, and then you progress from that point. So, so this is like very controlled way of executing communication across cluster components, and that's possible because we are simulating the network. The other advantage of simulating the network again is that there are I think it's not in this test, but you can introduce failures. So you can say that if I have a 3-node cluster, node 1 to node 2, you stop, break the network, or from client to a particular node, you break the network, and that allows us to then test all the failure scenarios. So see if this test is working for you. This is hello world test. Just take a moment to go through that story. I mean, this class can be named anything. There is not, it doesn't need to be storage replica. It can be anything. So for example, if you are implementing a replication algorithm like Raft, this can be a Raft node. If you are implementing Paxos, it can be a Paxos node. Any questions on that? Is it too vague? Was that too vague? No. Yeah. So you can dig down into that. I mean, just to quickly just mention, this framework is built on the principles of what is called as deterministic simulation testing. I won't go into details of that, but it's a pretty popular way to test distributed systems. The reason for this kind of techniques to exist is that if you know how production distributed systems are tested typically, have you heard of Jepsen framework? So Jepsen is a very popular framework, almost like a de facto standard for testing all the distributed system products. Like practically every database in the world is verified and tested with Jepsen. And the way these systems are tested, tested for consistency guarantees, is that you keep those systems up and running. Then you have your clients filing requests at these systems, and then you introduce failures, like you crash a certain node, you introduce a network delay, you introduce a clock skew, and what you expect is that even if anything like that happens, from client's perspective, you should not see inconsistent data. That's the expectation, roughly. Now, what happens is, if you randomly introduce, like, have you heard of chaos monkey or chaos engineering stuff? So, when you introduce failures randomly, it is very good for catching unknown bugs, like bugs that you might have never thought through or thought of. But it becomes extremely difficult to exactly reproduce the scenario that showcased that bug. And this deterministic simulation testing is a technique. What it does is that it uses controlled randomness in a way. So you keep the system running and introduce failures the same way, like what you will typically do with Jepsen or other tools. But you also do that in a way that if you hit a bug and you run the system again with same configuration, it will follow the exactly same scenarios or exactly same set of failures in exactly the same order. And then it allows you to easily debug some of these issues. So that's a different talk and workshop that I'm working on, but I just wanted to mention that. So now in that module 2, what we had was a versioned key value store, right? Versioned RocksDB store that we created. Now when we distribute that, essentially we have multiple nodes, right? Multiple processes across which the storage gets distributed. So what you can see here is we are using this Tickloom framework to create, now this is a different storage replica, but a 3-node cluster. And the number of nodes is essentially just defined by the number of names that you have in here. So it is create a storage replica server object. And you can see that any storage replica which is expected to run as a separate process in itself has a hybrid clock, like a wrapper over system clock that it will use, and then an MVCC store. And that MVCC store can be a RocksDB store or a memory store that we coded. So each replica will have structure like this, and very simplistically it will handle 2 requests, one write request and a read request, right? Now what is unique about the write request or any request that is sent across, request and response, is that each will carry hybrid timestamp. Like we looked at the rules of Lamport clock, right? So the primary thing with Lamport clock is the timestamp is carried in every message, and then each process, including the client, adjusts their own local clock with the timestamp that's passed across with the messages. So so you see that each request and each response carries this timestamp, and each request, when it's handled, you see that there is this merge clock that happens before actual read or write. And this merge clock is just a tick call from the propagated time. And writing to the store is exactly the same as what we did in module 2. Like you construct. Now the version time, that's one thing to note. So the time at which the write is actually executed is after that time is the process time from this process's hybrid clock is merged with the propagated time from the client, and your write will happen at that timestamp. And by default, read will also happen, at least in this case, with that timestamp. We see client.send method, client.write, sorry. It's hidden. And yeah, so one other primary thing or primary requirement whenever you have a cluster of processes and data distributed across is that you need to route each key to a particular node. So if we have like 3 key values, ideally we expect that each should go to a different node so that data is equally distributed. So, and that is handled by this client, and in the handling this we have coded that. So it's just a hash modulo, it's a modulo operation. So you take hash of the key, modulo the size of the cluster, which is 3 in this case, and whatever index you get, your key will be routed to that node. So, just to get familiarized with this, what you can do now is extend this test to a 5-node cluster, and with two more keys or a few more keys. So this particular test, you need to make sure that instead of 3, there are 5 nodes. Just to get familiarized with the code, because we'll The tests are passing for you, right? Because someone just said.
Yeah, Simon told that it's not getting.
Yeah. I mean, there's nothing much complicated happening there, so. So you have to just add two more names. So it will create two extra objects. And then you maybe create a few more keys. I think it's working for everyone. I don't think. Now, as you can see in this case, we wrote like 3 or 5 key values, and each went. Yeah.
Yes, there's a asserted line 56, right? So,
Okay.
can you talk a little bit about like what is that assert mean?
Okay,
What
I think
effectively
it's
what are we asserting?
no, that assert. Okay, that assert should have been removed. It's accidentally left. But what I was trying to assert was.
I mean, what is that? So, said another way, like what does a test for?
Right. So.
I mean, what does that assert test for?
So what I wanted to assert, that assert is not doing that, by the way. What I wanted to assert was if client timestamp is a particular set to a particular value, and each node has a timestamp set to a particular value, uh, when this message propagation happens, like write and then read, you expect that timestamp values to be adjusted accordingly. So that asset is not, I should have removed that. It's accidentally left there. Good catch, and thanks for catching that. By the way.
Yeah, no, I was just trying to
Yeah,
figure out that
because it doesn't make.
because otherwise the test is not. I mean, I think that's only. I mean, there is another assert equals, but
Right.
that again, actually the same question with that too, right? That, like that assert equals at 61, 62 is actually it's a similar.
Yeah,
so
I mean
it's saying that,
you could have said integer dot max value. Because I mean what we want is just that the value
yeah,
exists.
so I was trying to figure out how that value of 1000 there and the value of 5000 in at line 62.
Yeah.
No,
it's a
like how did those come up?
accidentally left out things.
So 56 is accidentally left.
Yeah.
What
Or
about
even
61?
that, because I had initial code where I had said
Okay.
explicitly set clock values to be 1000, 2000 and 3000. That's why I was
Right. So because I thought
that's
that
why I used
the
values
TS
higher than those.
Yeah, so the TS, like we will usually supply a value for TS in order to test some condition.
Right. So on 61, it just wants to get the latest value. So it can be any
So
like highest
value
value.
greater than
Any value greater than
2500, right? Because up there we created map of say.
no, but map is just a value.
Map is just a value.
Yeah.
So that is different.
Yeah, I should use better examples, I think. Yeah, those integers are confusing because your timestamp values are also numbers.
No, I mean at first glance it appears, but anyway, it's
Right.
fairly clear. But then so far we haven't.
Haven't asserted here on timestamp.
Yeah, right.
Okay. It's all happening internally. Right. So this was just to demonstrate that when you create a storage implementation on top of a networked storage implementation,
Right.
which is a distributed one,
Right.
you combine your hybrid clock and
Yeah, exactly.
MVCC.
I that's what I thought. That
Right.
Because that test is not making apparent that what is the behavior we want to assert. So
Right.
I was trying to.
That test is
place
just demonstrating routing of keys.
routing of keys. Okay.
Not the propagation of hybrid timestamp.
Right. Not the
Yes,
propagation
yes.
or not even or not yet the any possible or potential ordering.
No,
Between
not
those.
in this. This is just routing to different nodes. Yes.
But then, so on that note, so then how do we, I mean, what part in the test establishes that it is actually different nodes? Or the different nodes is by setup? Because we say
Different nodes is by
storage
setup.
node 1,
And
storage node 2,
and what we are asserting,
node 3.
we are directly asserting on the storage
so
nodes.
if you ignore the TS, then it basically asserts that you read whatever you wrote.
But you are writing from the client, which is routing to those objects,
To
and you are
the
asserting directly on objects. So
Right, correct.
it is just asserting that the routing is happening.
Yeah, correct.
That's it. Yeah. So,
So that just means to say that that test will pass regardless of the TS value for now.
for now, yes. Right. So as we saw, each of those key values, they are now living on different servers, right? Now, in the morning, we heard things like transactions and atomic commits and stuff like that. Right? So right now, what's happening is that each write is happening independently, right? So account 101 is getting on the server independent of account 202 request that goes on server 2. But let's say we have a requirement that these three key values, they are going to all different servers. They should either all be stored or nothing should be stored. So that's like a typical atomic commit kind of a requirement. Then obviously this basic implementation that we have, it's not supporting that, right? So right now what it's doing is just individual independent writes. But if we need an implementation like that, then we need to introduce a concept of transactions. And that module 4 that we have, and you will see a lot of
There is a message on grid that you are not sharing your screen.
sharing the screen. Okay. Cool. I think I will show them now. All right. So you can see that module 4, now just for read and write, you see like a bunch of different things that are out there, mostly related to transaction. And what we'll see now is how transaction is implemented on top of this basic distributed key value store. Now, two crucial requirements for transaction. One is that in our storage replica, and that's representing any database that you can think of. The way write request is handled is that whatever is written directly goes to that MVCC store that we had. And the way read requests are handled is that reads are directly happen on the MVCC store. So there is only one store that we have, right? Each read and write happens on that store. Now, if we want to support this concept of atomic commit, then we can't do that. And the reason we can't do that is that any write should not be exposed to any other client unless that node is sure that all the other nodes have also stored this value. Right, so I think I will try to go through. Okay, no, the slides are very bad. I mean, I will use them, but let's see if they are of any use. But you got the concept, right? So client is sending requests to node 1, then node 2, then node 3. But there is no way for node 1 to know if node 2 and 3 have stored the value or not. And for that reason, typically what we have is there is a need for an intermediate storage. So each node, instead of directly moving writes to the final store from where they are read, you create an intermediate step gap kind of a storage, and all the writes are accumulated in that storage. And only after all the writes are successful, someone needs to tell each of these nodes that everything is done and now you actually commit. Commit in the sense you now make this write visible to in your main store.
Sorry, can you rewind maybe 30 seconds back? So
Yes.
what is the problem? So whatever you just described is a solution or solution to what?
A problem. So the problem is that the way a naive implementation of read and write happens, like in this case, is there is only one
distributed KV storage.
Yeah. So this storage replica, right? So storage replica has one place where all the reads write go to, and writes go to, right? Now, any write request directly puts values into that store. Any reads directly read from that store. And this is a problem because if you need to wait or if you need to be told by someone when to actually write this particular value so that it's now final, you need to keep that somewhere else and not on the final key value store which is exposed to your reads.
No, maybe you'll have to repeat that part.
Problem is with the replication.
No. We are not replicating at all.
Yeah,
Okay,
this is just one node. It's just
Maybe I
three
should
different
draw it on
nodes.
the.
We're talking about insert for a distributed loop, for a distributed set. Insert per. If the writes are
Not
set
insert.
from at least
So
two.
there is no quorum as well. So there are three nodes, right? N1, N2, and N3. Now there is this client. It's writing to this, say K1, V1. It's writing to this K2, V2. And it's writing to this K3, V3. Right? So this is the basic implementation that we have. Now this is managing a key value store. This is managing the key value. This has that key value MVCC store, and this has that MVCC store. Now let's say there is another client, C2, and the atomic commit requirement is that if this client is reading now K1, it goes to N1, this client should not get anything because let's say if we don't know what happened here, then this value should not be exposed in this key value store, right? So that's the requirement.
Like
If-
so, also I think what is in that diagram? What is implicit is that write K1, V1, write K2, V2, write K3, V3 are all part of one
One
transaction.
transaction.
They are part of one transaction.
Right.
I mean, I did not
Yeah, that's
introduce the
not,
transaction concept there, but yeah. I mean, in the naive implementation, these were all three separate writes.
right, correct.
Now
So
we want
that's
to
a
club
live
them.
implementation. So
Ah.
what you are describing is only applies if we want
If we
transactional.
want, yes.
Because otherwise it's
Otherwise
okay.
it's fine.
Otherwise
Yeah,
there is
yeah.
no requirement being
Yeah,
made.
okay. So that was the missing part. So
Mm.
that's what when you asked me to rewind,
Ah,
because I said if the requirement is that all three should
yeah, correct.
go atomically,
Right.
or not.
Yeah.
Now, if the requirement is that is like this, so that we have this atomic transaction, then a write that's handled by these nodes, they cannot be exposed just like that, right, to any other clients making the read. And so they need to be stored somewhere because you still need to remember that this key and value was written to me. So you require a placeholder where you will store this K1, V1, K2, V3 key values. So on each replica node or each storage node, we require this kind of a placeholder where we keep intermediate writes. The other requirement is that someone needs to tell now each node when everything is successful. So if all these writes actually go through, then someone needs to tell these guys that done.
So, sorry, but one more, I think maybe it's representational or maybe it's more fundamental. MVCC store is, I mean, it's a single store, right? Like,
As of now, it is a single store.
so even in that, even in there.
So it doesn't need to be. I mean, you can actually have these two as two separate stores.
No, I mean, the one for N1 and the one for N2. Those two things that are represented over there, they still are pointing to. Oh no, wait. This is actually N1 is one node. So
N1 is one node. So they are separate
they are
servers.
separate. Okay.
They are separate servers. Yeah, they are not representing one.
Right. Okay.
Right. So simplest implementation is that this client tells everyone that done. And when you receive done, you move data from here to here. But obviously this is not as simple as it looks, because
but how client is sending that to N2 and N3, so it not to one single.
no, it doesn't need to. So someone needs to decide when everything is done and everything is successful. It can either be a node playing that role on behalf of client, or it can be client itself.
So are we talking here of database like K1, the leader is N1 and
So we are not. So
we
are not discussing leader at all. We are not talking of replication. So leader comes into picture only when there is replication. Typically, in case of a transaction like this, you have a transaction coordinate. So terminology is slightly different.
But that coordinator is also part of the vector, right?
It doesn't need to be.
Okay, doesn't need to be.
Doesn't need to be.
So this is just for understanding purpose, right? But in the
This is for understanding
actual distributed system, data will be written always to the one node, and that node either it is coordinator or either it is leader, and then that will take care of lifting it to the.
No.
Okay.
It will never happen. Actually, in distributed systems, data will never go to one node, and from there it distributed. The reason being, you distribute in the first place because data is too large to be managed by one node. So you will always try to minimize the need for any intermediary on the server side, and you try to go to individual servers from the client directly.
But
so
it won't be acknowledged back to the client unless it is replicated to the minimum core.
So we are not talking of replication at all.
Okay.
So there are two concepts and two totally different concepts. One is that of replication and one is that of partitioning and atomic writes across partitions. What we are focusing on is partitioning data on multiple nodes and then writing atomically across those partitions. Now the replication that you're mentioning is that typically you will have a cluster for this, a cluster for this, and a cluster for this. So it will be more nodes like this. And they form a smaller leader-follower setup within themselves. So a single write that we are representing here it actually becomes a replicated write across this set of nodes. And then that terminology of reader comes here, because then a write will be successful only when it goes on the forum and stuff like that. But even without any of this, the need for atomic write across partitions exists. So irrespective of whether you have replication at each of these places, or you don't have replication at all.
Okay, so just for my understanding, do you have any system in the any system which implements exactly this pattern where client need to write it to the multiple nodes?
All the system, all the distributed databases, they work like that.
No, but even if you take example of Cassandra, right? So
Yeah.
Cassandra, every node in the Cassandra clusters, is capable of serving the read and writes. So if their client doesn't need to write it to the each node in the Cassandra cluster. It just write it to the one node, and then Cassandra take care of replicating it across all the nodes. And even same in case of Kafka cluster as well, right? There also data goes to the leader, and leader take care of replicating it to the followers.
No. So I think there are two concepts as I
He is
said.
talking about atomic transaction.
Atomic
Atomic
transaction.
write. So you
So
have
there are
replication.
right. So there are architectures, and possibly Cassandra is one of them, where instead of directly, so here routing of a decision that K1 will go to node 1 and K2 will go to node 2 and K3 will go to node 3, it is done by the client SDK that runs on the client.
So maybe it might be using consistent hashing or rendezvous hashing.
Yeah,
Okay, that's why it went to end-to-end.
Right. Now there is a subtle requirement there that, yeah, okay, I see where you are coming from. So for client library or client SDK to be able to make this call that this key needs to go to this particular node and stuff like that, it needs to have all the information about the cluster topology, right? And typically in case of Kafka or Yugabyte or other databases, you have client SDK which talks to the membership service which maintains all the information about the cluster. In case of Cassandra, client library doesn't do that. So the expectation is that your client talks to any of the servers, and this cluster membership information is only on the server nodes. So they route the message. Right?
So what you're saying is, in case of Kafka, the Kafka client library takes care of writing it to
Kafka
the...
client library takes care of that. Yugabyte client library takes care of that.
Okay.
There are other typically databases which you expect to be running on the server side, like behind, like maybe your services using those. They will have client libraries which can fetch cluster topology talking to the membership service and do that. So Kafka, Yugabyte, I think Cockroach, they all do client SDK deciding where to go. In case of Cassandra, the topology is like that clients talk to any of the nodes, and those nodes route to different nodes.
Okay, yeah,
So I
thanks.
think for one other instance of what he said, what Shrikant you said, is for example, I talked earlier about Citus, right?
Right.
Citus has Citus is also actually distributed Postgres, right? So it is that partitioning, like it is basically a way to partition your data set over multiple servers.
Right.
Now Citus has something called a designated coordinator.
Right.
And it's a coordinator that maintains that map and
Right.
and so it basically maintains a PG disk node or whatever and it sends it to them.
Right.
Then Citus they shipped another thing called MX that they called MX. MX. I forgot what MX stands for. But there in MX mode, then instead of having a designated coordinator, which could be the single, which could be a bottleneck,
Right.
client can connect to any of the nodes and do what you just described.
Right.
That's, I think, I just want to share that that's one case where the client SDK does not have that.
Does not.
Citus, the client SDK is Postgres SDK.
Right.
So Postgres SDK,
Won't know about the
vanilla
topology
Postgres
of the-
SDK doesn't know about the
Also
horizontal
topology.
scaling. It doesn't know the topology.
But whoever routes the individual write requests to independent servers, that entity will decide when the work is done, like when all the writes are done. And then it needs to trigger this, what is typically called as a commit, transaction commit rate. So a transaction, typically even when we do a single node transaction, we need to demarcate the transaction. So we say begin, then do write and read, and then commit or abort. This is the typically how transaction is demarcated. Transaction reads and writes.
Here, client is coordinating full transaction.
Client is coordinating. So typically begin, marking your unit of work, begin, commit and abort, it will be done at the client. Now what happens as part of this begin and commit is handled by the server. So when you invoke begin, it needs to record somewhere that okay, there is this transaction which is getting started. Then when you write as part of that transaction, whoever is bookkeeping, like this write is part of this transaction, it needs to do that. But this loop or this lock, which is demarcated by begin and commit, that will be always on the client. Now, in the naive implementation, like simple implementation like this, which is not, if we let's say just do an intermediate storage where we do writes and then we expect a done message, and when we get a done message, you move the data across. This is not fault tolerant. The reason being, if only one done succeeds and these messages get lost, then there is no way for N2 and N3 to know that, what happened to this transaction. The other challenge is that if client itself crashes after first done, then you are almost screwed because you never know when that client is going to come back up. And one of the reasons why two-phase commit protocol is it's called a blocking protocol, right? Because imagine that we are not talking about locks, etc. But imagine these two nodes have taken lock on K2 and K3, and this node crashes. Then you cannot release those locks. You are like locked forever because you don't know if this actually crashed or it's just that we are disconnected from this node. And in no case it should be assuming that the transaction actually committed or aborted. It cannot take any decision, and that's the reason it is called blocking. Now obviously this kind of blocking transaction implementation is not acceptable in any distributed system. And why it's not acceptable is that actually there are very interesting reports and talks about what actually happens in a data center. And if you see the number of failures that, so a data center of Google scale or Amazon scale, let's say it has thousands of servers, and it's very complex, the way the servers are stacked into racks and the way they are power supplied and they are cooled, and the way the network cables are set up and stuff like that. The expectation is that at any given point in time, there is something called crashing. So either disk crashing, either your network switches getting flooded, or anything of that sort is happening. And one of the key design principles, and if you see practically any distributed system, like a distributed database or things like Kafka or Kubernetes or anything of that sort, the key design guideline is that it should remain operational even if part of the system is always down. So if you, let's say, have a 10-node cluster and 3 nodes are always going to be out, and those 3 are always variable, so it's not like same 3, it will shift as you progress. And in that kind of a, if that's the requirement, then we can't have this kind of implementation, right? And that's why two-phase commit, particularly if you remember, NoSQL databases, when they were first introduced in all these cloud businesses, they were eventually consistent. None of the NoSQL databases implemented two-phase commit. And eventual consistency was actually advertised as, and I mean, one of the reasons for this kind of a complexity that two-phase commit will introduce this kind of a blocking behavior. The way to work around that, and what most of the, I mean, not most, all of today's distributed data systems do, is that they don't rely on client to keep the state of what is the status of transaction. So what happens is, so what happens is, when client wants to atomically write something, and that means create a transaction, one of the nodes in the cluster assumes the role of transaction state manager. I mean, I won't call it a transaction coordinator, but a node that's responsible for tracking what is the state of the transaction. And the way then that interaction happens is that client first talks to a node saying that begin transaction, and it can be any of the nodes in the cluster. Just like we saw that the way different keys are routed to different servers, we just take hash of the key and do a modulo number of clusters operation, right? So the way it's typically done is that let's say we assign each transaction a transaction ID, which is, let's say, just a UUID, and we do the same modulo in operation, saying hash of UUID modulo the cluster members, and whatever index we get, we route that begin transaction to that node. So each of these nodes can potentially act as transaction state managers or transaction coordinators, right? I'm avoiding the name coordinator because it is coordinated by client to begin and commit of the transaction, but the state is managed on any of this. So let's say first, whenever a node gets begin transaction kind of a message, it makes a note that there is a TXN ID 1, which is in a pending state. it just makes a note of that. And then it does read and write, just like we did before. So write K1, V1. One additional thing that it does now is it also sends the TXN ID. So every write and read will get a transaction ID. And then this write will go in a intermediate storage. Again, yeah, there will be a TXN ID. And after all the writes are done, this client will again send a message to whoever is the transaction coordinator saying commit. TXN ID. And then it will mark this particular transaction as committed. Now the advantage of this kind of bookkeeping is that now after commit is done, you can, commit is sent to the transaction manager or transaction who is tracking the transaction. There are again multiple choices. Either you can tell this node who all are the participants, because you know all the keys which are written as part of this transaction. So you can very well send that list to this guy, and then it can propagate commit messages to everyone. Or you can send commit messages to each individual nodes from here. Now how this avoids that blocking situation is that, let's say all this, again, they get lost and this client is crashed. You still have information on each individual server that there was a transaction ID 1 which was writing this K1, V1 and K2, V2. That information is there on all the servers where that write has happened. So whenever any other client comes to these nodes and tries to either read or write, so now there is, let's say, this C2. It comes and tries to write or read K1. What this node can do, and does the same here, and it can be read or written. Any request for that particular key. Because each individual node now knows that this K1 and this K2, they were in the intermediate storage, and then there is this transaction ID associated with them. They can use the same routing logic of taking hash of that transaction ID to figure out which node to go to. And they can ask, like this node will ask itself, get me the status. And this node will ask this guy, get status of T1. And if the transaction was committed, that means there is a commit, this transaction is marked as committed on this coordinator node. Then at this point, they can move the data from intermediate storage to to the final storage. So have you heard the term read repair? Only people who use Cassandra might be aware of that. Right? So it's the same concept. You care about any unknown or incomplete result only when there is some other client interested in that key or value. So you resolve those transactions in case of these kind of failures. Another failure.
No, she's trying to show that.
Yeah, I was
Oh,
just
you are
trying
to show this?
Yeah.
It's very difficult. No, it's very difficult. But I'm almost done.
Yeah, okay.
Yeah, I didn't realize actually.
No, it's fine.
Right. So this is the basic implementation of how this is basically how transactions are implemented in distributed storage. Practically, Kafka does something very similar, and you provide additional fault tolerance. As I said, because if each of these is like an individual replicated set of objects, set of servers, then even when they say this goes down, your transaction state is actually available on one of these, right? So this is basic transaction implementation. Now there is additional requirement, obviously, and the additional requirement is that we right now talked about only single transaction that is happening atomically. So we just talked of atomicity or atomically committing multiple writes. But imagine that there are multiple clients, each trying to write and read the same K1, K2, K3. Then another requirement that transactions by default have is that of isolation, right? So no two concurrent transactions should be able to modify same keys. They should not interfere. And typically, historically, how this is avoided or how this is implemented is by using locks. Like even in our concurrent programs, we use synchronization and locks, right? So let's say this, like each write request also then takes lock on K1, K2, and K3. Simplistic implementation. The problem with locks is that in real applications, almost 80% of the requests are typically read requests, and only 20% are write requests. So if we try to take lock on every read and write request, it impacts your throughput and latency. So what most databases try to do is they try to avoid taking locks on the read requests. So they are designed in such a way, or they prefer designs in which read requests return immediately without bothering about any locking whatsoever. And if you now need to implement transactions with this constraint that read requests ideally or in read requests should not be taking any locks, then that's the algorithm for transactions which is called as snapshot isolation. So you might have like practically all data, like even single node databases like Postgres and Oracle, they implement snapshot isolation by default. So your reads don't take locks, write requests do take locks. and the default way to implement that read requests do not take locks and only writes probably will need locks, is to have multiple versions created for every write. So the MVCC store that we looked at, where every write goes as a separate version, is naturally suitable for transaction implementation, which is this snapshot isolation kind of implementation. So what we'll do now is there is this module 4, and what it does is it implements basic snapshot isolation on top of the distributed key value store that we implemented. It will
The failure cases in this transaction, are we going to discuss that?
Yeah, we'll see that. But the key concept is that you keep transaction state on one of the nodes in here, so that even if your messages get lost from the client or client crashes, there is a way for other nodes to consult that bookkeeper or transaction manager and resolve those transactions.
So you were talking about the read repair.
So the concept is similar to read repair. So you trigger that resolution only when there is another read or write request for the same key.
Okay, so here basically, let's say you said like you will create a copy. Let's say write K1, V1.
Right. So
So you created a copy on N1. Then you created a copy on N2.
Yes.
Then you said commit.
Then I said commit. But commit did not go to N1 and N2 directly. I mean, it went to N1 here because transaction ID was mapped to N1.
To some coordinator.
To some coordinator. And that coordinator is keeping this transaction state.
So now what will happen internally when you say commit to this coordinator?
Right. So in the happy path scenario, you commit to coordinator, and then either coordinator tells all the nodes that transaction is committed, happy path scenario, or client can tell everyone that.
Here you will need a two-phase commit, right? So everyone has to.
It is a two-phase commit.
Yeah, it's just, but you said we are not using the two-phase commit.
We are not using locks, but it is two-phase commit. So there are two phases, right? We are first telling everyone to do something, and then in the second phase we are communicating the decision of either. So it is two-phase commit.
When the client initiated commit reverse, right? Let's say commit happened on servers.
Yeah.
The client crashed.
Yes.
Right. That is also considered as a commit, right?
That is so. So as long as this commit reached this transaction, whoever was doing bookkeeping for that transaction, then it's commit.
Commit, right? Even
when client
for
crashes.
response.
Yes.
And when you talk about intermediate storage, right?
Yeah.
It's kind of a LSM tree append with
So
transaction.
it can be anything. It can be really anything. I mean, in our case, we can use the same, or we will use the same MVCC store, just another instance of it. Or other way to, so it's again a design choice. What you can do is, you can keep this as a separate store, or you somehow mark this record saying that this is a, because this has transaction ID as, so you mark this as a temporary record or in-flight record or something like that.
So what does the actual one system does? I mean, they create a different store or they maintain in the same store? Just a page.
So actually, both the things are done. For example, Yugabyte explicitly mentions a different store, what they call as a intent store, like provisional records. What that is a provisional record. They maintain a separate RocksDB instance for that. CockroachDB manages it in the same table.
That will be
All the databases also they do it in the same file.
So
So what you would expect is that intermediate to final storage movement needs to be atomic. So it should not break like in between. And that's where that write batch that we looked at, right, the write batch interface, that's used when you move records. So
just one question, you already have a state management, right? Transaction successful.
yes.
So even if that fails,
Yeah.
I know in the next read cycle that, as you said, read repair, that ID is done. I mean, it's
Yeah. No, that is there. But its question was, I think, if it fails in between, like you are moving data and it fails in between, then you again have a inconsistent state, right? Because maybe half the records are copied and half the records are not. So if there were like multiple writes stored in an intermediate store and you move multiple writes one by one. So when you are moving, it needs to be atomic operation. Yeah, that's the constraint.
People talk about consensus raft. So where is
consensus
here?
So it is not. So consensus is required when you have exact same copy of data on multiple nodes. Like within, like let's say this K1 V1 is on node 1. Now it can have multiple replicas, each having K1 V1. And the replication algorithm that runs between these replicas, that's raft or Paxos. That is the consensus algorithm. But two-phase commit doesn't need consensus. So yeah, okay. So one, and that's a very good, that's a very big difference between consensus and two-phase commit. Two-phase commit, the way we discussed, happens on heterogeneous data. Like we are talking about atomic commit of different key values, different data items, across different partitions. But there are different data items. Consensus, you will have exactly same data across all those.
In our example, we have not considered 2PC, right?
This is 2PC.
No, we are directly saying we are not acknowledging, right? Every node has not acknowledged that they will write it. We are just
because we are directly
writing.
We are directly writing it. But it is 2PC. Because there are two distinct phases. I mean, every write you can consider that as a prepare because you are directly writing, but it's not exposed.
So you are beginning transaction, writing, and directly committing.
And then committing, yes.
And that state management is getting replicated. That's the reason it's highly reliable, right?
Yes.
And that's where the raft comes in picture.
Yes. So anytime same data needs to be replicated across multiple nodes, raft or Paxos or any other consensus that comes into it.
How does the both works together then?
Who?
The transactions and then the replication also.
Yeah. So any data written on any of the nodes, that's replicated with raft. So this write request, when it's handled on this node, it will use raft internally to copy it on multiple nodes. This begin transaction request, when the transaction record is created, this will be replicated across all the nodes by raft.
Okay. So I was just like thinking like simultaneously two things are happening, right? Like
Simultaneously two things are happening.
There
Yes.
is a
Yes.
communication between the nodes also, and then in between the cluster there is a communication
Yes.
between the.
Yes. T is it.
Unmesh, raft also needs 2PC, right? So there is another 2PC.
Raft does, okay, yeah, I mean there are any consistent replication or any consensus algorithm needs 2PC, but raft-like algorithms which are leader-based, they are optimized that if there is a stable leader, okay, yeah, but yes, it is 2PC. But I an optimized 2PC, you can say, because the data items are exactly the same copies. Okay, so yeah, but that's a good point, because you can imagine the number of messages getting passed across nodes just for doing like single atomic operations, and that's the reason whenever we have these nodes placed across regions, it can become extremely expensive operation in terms of latency and throughput.
That box do draw for, and when we can call it as a tablet in YugabyteDB, right?
Yes. Tablet, shard, partition. I mean, in case of Kafka, that will be your partition, topic partition.
So what happens when we add?
Okay, that's a totally different. But yeah, okay. So, but that's a good question, because what we assume so far is that the cluster membership is not changing, and if we change that assumption, then there are a lot of other things that need to happen. One is that when that thing needs to happen, you essentially can take two decisions. One is you don't touch data on any of these nodes, and just like all the new data starts considering that additional node to be part of the cluster. But that doesn't work. That doesn't work if you are doing like this hash modulo number of servers, and that is the reason there is this concept of partitions or logical partitions, and then you do hash modulo on a logical partition that never changes. And that's also the reason why logical partitions are typically lot higher than number of nodes. So you will have like 100 partitions, 250 partitions, and then even when you add more and more servers, that mapping from key to partition, which is computed by that modulo hash modulo, that doesn't change. And then you can behind the scenes maybe move partitions across the cluster.
Can we discuss a bit about that first, that consensus? How? Yeah.
Consensus.
Yeah. Okay.
Over TC. Yes. Yeah, but that's actually that's a different workshop that I have, because it has a lot many concepts. Because very similar to what you need to do, like begin, write, and stuff like that.
In that workshop, are you just going to discuss about the
Paxos and draft.
Okay, to the English.
Yeah.
When is that?
Doing one for orally on 7th April. No, 8th April.
Okay.
For oral.
No, orally, it's online.
Okay.
Yeah, but draft is essentially similar thing happening. So we'll break for tea. Then we'll see in code how all this works and what happens in case of failures. But we did not discuss transaction isolation yet.
When is that workshop planned for next week? This Rootconf?
Which one?
That consultancy.
It's not planned. Not planned. Huh?
It's planned.
No, 8th April is for orally.
Okay.
It's online.
For you have not planned for this.
Not planned for this, but we can do
You have
one.
to, yeah.
Yeah.
Maybe online.
I think you need to power on your laptop is slightly charged.
Oh.
This charger?
No, I have charger.
I'm just going to check this.
Don't have charger. No, I have charger. There is no charger. तर त्यांनी इकडे काही ठेवलं नाही का? How am I supposed to charge?
Or we can bring your laptop here to the
हाँ.
table. I'll also check how to turn on the webcam.
No, I think now I'm
You're back to ID of this.
back to ID after this. Yeah. Yeah, I think those things were a bit complicated.
Yeah.
Cool. So, yeah. So I'll recap quickly in 5 minutes what we discussed. So first thing we discussed was whenever there is a need for atomic commit, that means multiple reads and writes happening or spread across processes or nodes, doing work as one atomic unit.
This message has no audio.
No audio, no. I think it should be. I mean, it was on mute, but now it should be there.
It's coming on.
Audio is there, right? Yeah, it was on mute initially, but right. So if we have that kind of a requirement, there are multiple things that we need to build on top of the basic key value implementation that we saw. The first thing that we said is that any writes that are going to individual nodes, they cannot directly be exposed to the final key value store and to other clients. And someone needs to track when everything is successful, all the writes and reads are successfully done, and communicate that decision to each individual node. Now, if that tracking of success of that atomic unit of work is done by client, we said that there is a possibility that after everything is done, client crashes, or messages from clients to individual nodes, they get lost. And so we can't rely on client to track that state of what's happening. Client can still coordinate because client is the one who knows when everything is done. But the state or tracking of everything is successful or not is then done on one of the other servers, which is chosen as a transaction manager or transaction coordinator. And a typical flow then looks like is that any client, before beginning any work, they choose a transaction identifier, which is typically just a UUID, a unique ID assigned to the transaction. Then based on this transaction ID, maybe just do a hash modulo n on the cluster members. It picks up one node, which then it designates as a coordinator for this transaction. It sends begin transaction request to that particular node. Now, each cluster node now manages this extra state. So apart from the key value storage that we have, there is also this transaction state storage that we need to have. And after this begin is done, it does read and write to individual servers, with one difference, that it tags each of that read and write request with the transaction ID. So whenever these individual nodes do intermediate storage or provisional storage of these writes that are happening on the servers, they also store transaction ID along with that. And after everything is done, if it's successful, and we will see when it can be unsuccessful, and that's where this managing concurrent transactions and transaction isolation point comes in. When everything is successful, the first thing that client does is sends commit message to the node acting as a transaction coordinator, so that this transaction record is marked as committed. And after that is done, it can choose to send commit messages to all the individual nodes, telling them that everything is successful, at which point the data is made visible to other clients. And if you are storing it in a different provisional store, move that data to the final store. But because we are now tracking transaction state on one of the nodes, even if client crashes after this commit is successful, commit message is successfully written, or messages get lost, the individual commit messages to the servers. Each server, along with each provisional write record, has enough information to be able to ask the coordinator which is tracking this transaction, what is the state of the transaction. And it can do that whenever there is another transaction or another client trying to read or write that particular key, and which is, as I said, very similar to the read repair mechanism that happens, right? And other thing that we discussed, again, we are not talking it here, is that any state managed by each individual server is typically replicated across multiple nodes, and that replication uses consensus algorithm like Raft or Paxos. But two-phase commit, I mean the mechanism that we just discussed is two-phase commit mechanism. There are two phases before data is exposed to other clients. The first is provisional write, and the second is when you commit that provisional write. And we'll see how it looks in code now. So I will just move my laptop to that other place. Cool. Right. So if you see, there is this module 4, which is distributed transactional KV. Sorry. What's this? And maybe we can go through the test. So there is a test called transactional storage replica core flow test, which is just demonstrating this core flow of begin, read, write, and commit. Again, this is happening on a three node cluster. So I will walk through the code to show what's happening. Right. So here we are creating the cluster with three nodes, just like what we did in the earlier modules. And this is like a representing a distributed key value store. Each node managing a set of keys. Then there is a client now that we have, which is called as transactional storage client. And the way it works is that we are always expected to say begin or call begin transaction, and let's see how that begin transaction. So if you see how begin transaction is implemented, it's sending the request, begin transaction request, to the node that it picks up based on the transaction ID. And it is exactly the same logic that we have for picking up the replica for key. So this is the client side. The replica side which is this class representing the replica. You can see that there are, so our initial the simple storage replica had only one MVCC store and hybrid clock, right? I mean, that was the minimal things that we had. Now it has, you can see that it has two different MVCC stores. One is called as intent store and the other is called as committed store. And you can imagine what we discussed, like storing intermediate writes or provisional writes which are not exposed to client. That is what this intent store is for. And then there is an in-memory map of transaction ID to transaction record. Now you can use, actually in this case, there is a comment there why it's in memory, because it should not be in memory, because this is like the key information and the source of truth of what for what happened to a particular transaction. So it should not be in memory. It is right now kept in memory. I mean, just for the sake of it. What you will typically find is, again, there are multiple choices and multiple design decisions that you can take. One is that you use a storage like RocksDB even for these records, and that should be done. I should have done that actually. But the other is that we talked about replication, and any write happening to any node is actually replicated across a set of other nodes, and that is done by implementing algorithms like Raft. So you can choose to rely on Raft, and Raft maintains whole history of all the writes that happened on any of the nodes. So if you rely on that as your backup state, like the event store you typically have, then you can keep this in memory and reconstruct that in case there is a failure. So that's the reason I just kept it in memory for now, just so that we can discuss that particular point. But this replica, now see the number of messages that it supports. So apart from a simple read and write, each node now supports a begin transaction request, a commit request, something called as get transaction status request that it needs to support if someone needs to know about the transaction status, any of the nodes. And then there is a resolve transaction request that we'll talk about. I mean, the resolve transaction is essentially a commit request that is sent to individual nodes. We can consider it that way. But begin transaction request, essentially, like any other request, you see that every request that's handled it does that hybrid timestamp merge, right? And begin transaction request needs to do that as well. So this is the first exercise that we have, that we need to implement this method to create a transaction record in transactional storage replica. So begin transaction needs to create a transaction record. And after begin transaction is done, you okay, this test is just for testing transaction records, but yeah, I'm just, yeah. So after you begin a transaction, then you do all the reads and writes. And the way write request is handled in this transactional storage replica is also now very different. I mean, slightly different, but. So if you compare this with the earlier storage replica in the previous module, there we were writing it to the single MVCC store that we had. Now here there are multiple things, and we will talk about that. But the primary thing that's happening is that okay, I have that as an exercise, but it writes this record into that other MVCC store that we have, that intent store. So it is not actually writing it to the store which is committed store. And again, this is a design choice, whether to use two separate stores or same store and just mark this record as a in transit or in process, and filter that then while you read. And this is, by the way, a very common pattern, that you mark records as unknown state, and even if you keep that as a like in your primary store, when someone is reading it, you ignore those. Good example is Kafka. So Kafka also implements two-phase commit, and it does exactly the same, because Kafka, there is no other intermediate store. There is only one log that it has, but it keeps track of records which are in flight, I mean, which are not committed per se, and it filters those records, so they are not returned to the user when or to the consumer in Kafka's terminology. So this is first change, that writes are not returned to the primary store, and the other is just a minute. I just want to. I'm just finding the place where, yeah. So when the resolve. Okay, I'll just walk through the flow. Right. Yeah, I have fragmented test, so I don't know. I mean, I thought that will be easier, but I think having a single test that goes till commit is easier. Yeah, so this test is that. So after you do a write, so begin transaction, then you do a write, and then you do a commit. And when commit request is sent, again, it's sent, as you can see, to the transaction coordinator for this transaction, and that will be one of the transaction storage replica instances. And commit request updates that transaction record that we created in the begin transaction, marking it as committed. And then it can send requests to all the participant nodes saying that whatever intermediate storage you have, now you can move it to the intermediate to the final storage. Now this request can get lost. I mean, the individual nodes that resolve request, it can get lost because each individual node I mean, that was the other part of handling the right request. You can see that there is this check and resolve intents method. So anytime you handle a read or a write, if you find that there is a intermediate storage which has an entry for this particular key, you go to the transaction coordinator and ask if I need to resolve this intent or not. And yeah, this is where it's so you see that there are two cases. One, if the transaction is still pending, so you don't know if this transaction was committed or not, and that means that it might be an in-flight transaction, so still to be committed. In that case, this provisional record actually acts as a lock because you are trying to write to something which is in-flight transaction. So what you say is that, okay, then I mark myself as a failure. So you return error to the user. But if it was committed, this is where you actually resolve that. So saying that, okay, this was a previously committed transaction. I move that data from so this is where it is moving that data and removing it from the intent store. So this is the whole flow. Just to familiarize with this, we'll try to complete those two exercises where first we create a transaction record and then we write to the intent store and then we handle the commit. There are 3 assignments. You can look at the solutions repo if you want to. I mean solutions branch, sorry. It will be easier. So do you want to do these 3? I think it will be helpful, right? I mean, just to get that flow clear in your head. Yeah, because it becomes very complicated beyond a point. Too many things happening in like single request.
difference between commit and resolve? Commit is just committing the transaction.
Commit is
but not
just
resolve.
marking the transaction as committed, and resolve is like to individual nodes which are managing key and value. The request that is sent. I mean, it is called as resolve. I mean, you can call it commit
No, I
only.
think in this code, the resolve is actually putting it into the committed store.
No, yeah. So resolve will put it into committed store. Yes.
And the commit is just
So,
mark it as committed.
so there are three stores, right?
Yeah.
So there is a transactions record store. There is an intent store, which is a provisional record store,
Correct.
and then there is a committed store from which the actual values are read. Right?
Yeah.
So commit, when client sends to the transaction coordinator, it goes to this transaction records. So it just marks that transaction record as committed.
It doesn't put it into the commit store. at that
Because
time.
no, because it might not be the same node which is handling keys and values, right? This can be different node.
Okay.
And then individual nodes are sent that resolve request,
Okay.
which then move data from
Got it.
intent store to committed store. So yeah, I will just probably, yeah. So the transaction record is essentially you just keep it like this. What I have in there. Oh my, it's already 4:40. Yeah, I will move quickly. Maybe I will walk through some of the interesting stuff, which are all the anomalies that are still there with this basic implementation. So this is basic transaction implementation, and we'll see why we are calling it a snapshot isolation, with one implementation piece missing from standard snapshot isolation implementation. But begin transaction essentially marks a transaction as pending, or it registers that there is an in-flight transaction which is pending. Then writes, when the write requests are handled, the requests are written only to the intent store, so they are not yet into the committed store. And when you handle commit, transaction, that's where you mark the transaction record as committed, and each individual node responsible for various keys is sent the resolve request. I mean, we are calling it a resolve request because in these data stores like Yugabyte and Cockroach, this is called as resolving the intent and moving the data to the committed state. But this resolve request, if you see when it is handled, resolve committed intent. So this is where they are moved from that intent store into the committed store.
So who calls the resolved request then? Client only calls the commit, right?
So client calls the commit, and then someone needs to communicate with all the individual nodes. That can either be done by client itself synchronously, or the coordinator can do that as well. Only thing is that no one waits for those requests to complete, because the way we are implemented, each individual node, even whenever it detects that there is a intent or provisional record, it will go and ask the transactions store. So this is the basic flow. Let's see what happens in the read request, because that's what makes it tricky. Handle transaction read request. Now read request in the basic flow, it reads from that commit store, and the way it reads it is, so each read request has a read timestamp. So whenever one thing that happens in this transaction implementation or a snapshot transaction implementation, snapshot isolation implementation, is that whenever we begin a transaction, there is a timestamp that is associated for that transaction, and all the reads that happen as part of that transaction, they happen as of that timestamp. So every read request will carry that timestamp, and every read that happens, it happens from the committed store as of that timestamp. There are a few caveats in here. One, have you heard of this term called read your own writes? So if I am writing to some node and I am reading as part of the same transaction, I write and then I read, the expectation is that I should get what I wrote, even when it's an in-flight transaction, right? This implement, I mean, if we directly go and read from committed store for every read, we will not achieve read your own writes transaction, right? And that is the reason we always need to go to intent store first, because it's a different store. Read from there, and if the provisional write that's there is part of the same transaction for which this read request is, we return that for that particular transaction. For all the other clients or all the other transactions, that record is not visible, but for the same transaction, that record should be visible. So you can see that when the read request is when the read request is handled, the first thing that it does is in the intent store, it finds if there is a provisional record for my own transaction, irrespective of the timestamp that's there. And if it finds one, it immediately responds with that value. So it achieves read your own writes. If there is any other intents, very similar to what we did in the write request, it needs to figure out if they are pending writes from already committed transactions, and then it needs to resolve the same thing. And after doing all this, that resolve will move data from intent store into committed store, and then it can read from that committed store. So there are a lot of things happening there. One thing that is different from the way writes are handled and reads are handled is that for write, we are actually making an entry into that intent store, right? We are making writing a record. And if any other transaction tries to write for the same key, we can easily detect a conflict that we are writing to this key, a particular value, and other transaction is also trying to write to that key, and we can say that this is a conflict and we return error for the other transaction. But when we are reading, we are not doing any check like that. And this is kind of a variant of, if you imagine those provisional records or intent records as locks. They are like durable locks, right? So those records themselves are acting as locks to make sure that no other write can happen for same key while this record exists. For read, we are not holding any locks. We are not checking for any conflict like that. So this is in part what snapshot isolation does. Reads directly go and read at a particular timestamp. We will just look at the place where this read timestamp is assigned. Let's figure out where the read is. Do you see a read request here? There is a test doing read. Yeah, so you can see that there are two read methods on this client. One is implicitly passing its own hybrid clock to the read request, but that I think is wrong, because for the entire transaction you need to have same timestamp, and that's typically when the transaction begins. You need to have that timestamp. But is this basic transaction flow clear? I think if you go to any of the open source database source codes, right, you will find similar flow of request handlings that happen. So there is one last thing, and I think we have 10 more minutes ideally, because we are close to 5. But there are certain anomalies. Have you heard of these transaction anomalies like lost update and dirty reads, dirty writes, write skew, read skew, and stuff like that? So snapshot isolation has one anomaly called as write skew, and even lost update if snapshot isolation is not done properly, like what we have done. So I have a couple of tests that I will just mention or show you what's happening there. So there is this. This is a very classic scenario of write skew, and what it is let's say there are two transactions that are trying to change state of doctor's status. So whether they are on call or off call, and if both transactions check read these two records, like transaction 1 reads Dr. Alice and Dr. Bob, and transaction 2 as well read for Dr. Alice and Dr. Bob, and they both read values which are saying that they are they are on call. And then ideally, only one transaction, when they are writing or updating that status, only one transaction should succeed, because otherwise one transaction will write something and other transaction will overwrite it, right? And that should not happen. No two concurrent transactions should overwrite values written by another transaction. But this basic implementation that we have of snapshot isolation, it actually allows doing that. And snapshot isolation, when you use snapshot isolation as a transaction isolation level in any database, it actually allows this kind of anomaly to happen. So typically in databases, even single node databases like Postgres, you will see that there is this serializable snapshot isolation implementation that does, which avoids. So if it's serializable snapshot isolation, this test should fail, because both transactions should not be able to update. Only one transaction should succeed. There is another test that I have, but I will just point. Yeah, there is an example of lost update test, I think, but I'm not sure if it's okay. Yeah, it's green, but that means that lost update is happening. So it's like ulta test. But so this test should also fail, because our implementation currently is allowing lost update to happen. But two important things that I just want you to keep in mind while you explore this code base later and read more. One is that distributed transactions, this two-phase commit that we just saw, it has this multi-layer storage. Like you need to have a provisional storage and then a final storage, and a way to track transaction status across the cluster, which is fault tolerant. So you can't rely on client to keep all that state. And the second is that snapshot isolation, and we did not go into much details of snapshot isolation, but that snapshot isolation is possible in this implementation because each write is happening as a new versioned insert. And what that allows you to do is that you can read a particular version while maybe other writes are updating that record without need to hold the lock for the read request. Any questions on this? I mean, this was a bit rushed, I know, snapshot isolation. Yeah, but I like snapshot isolation itself will probably take a workshop of its own. But I think one of the hopes that I have is once you have this kind of a code base, and I will refine this, I think, because there are few things which are a bit confusing, like that set time for process is done unnecessarily in there. But I will refine it in next couple of days to make that snapshot isolation a little more explicit in the code base. But do use this while you read, like if you are reading books like data intensive application, particularly the transactions chapter, or using any database which is distributed and claims to be implementing transactions. I think this code base and whatever we discussed might be helpful in that. Cool. So I think we are almost, I think it's 5 o'clock, so we'll close for the day, but I think we can discuss I'll be here for half an hour more if you want to discuss anything. Is the transaction flow at least somewhat clear? because there are a lot of things that are happening there. Yeah.
Sorry, to go back to previous one, in the read, begin read method, that why are we resolving intent there is not clear, because it has to be done during the write.
No, but even so, the thing is that maybe I will go to the yeah, it is there. So the thing is that see, if you are in this state, oops, you want to,
Yeah, I'll do
okay,
it.
I'll yeah. So the question is that if this read request goes to this node and it detects that, okay, there is this intent store which has K1 V1 TXN ID 1, right? Why does it need to resolve the request, right? So let's say all this transaction happened and the transaction is committed at a timestamp say 10, and what it means, maybe I was not very explicit. So what it means is that when data is written into the final store, it needs to be written with timestamp 10. And let's say now another client at timestamp 11 is trying to read, and it detects that there is a provisional record, so tries to read same key K1, and it detects that there is a provisional record in here. If we are in a state where the previous transaction which wrote that K1 V1 was committed at timestamp 10, then this read is supposed to return that value, right? Because this is happening at timestamp 11. But at this point, it doesn't know if this provisional record that's there, it's actually from a committed transaction or not.
Because it is not yet deleted, it is still there.
It is still there, and maybe because these messages were lost or client crashed. So in that case, so anytime you see a provisional record, you need to always check the status, because there is always a possibility that it was committed, and you need to return that to client in your snapshot. So resolution happens in write as well as in read.
Just wanted to clarify on understanding.
Yeah.
MVCC, reads and writes are not blocked.
Yeah.
Right?
Yeah.
But write on same case blocked.
Yes, it is. And because of that, to avoid that lost update anomaly, there needs to be an additional check that needs to happen when you commit the transaction. And you have to make sure that when you commit, there shouldn't be another commit that happened at timestamp which is after your read timestamp.
Who drives that hybrid clock here?
So hybrid clock, as we said, it's continuously passed across. So this particular, yeah, I think this is the detail that I missed. But when the commit message is sent, right, whatever is the hybrid clock value at the node which is owning the transaction record, it is assigned here as a commit timestamp. So that is the timestamp which is assigned to this transaction.
So it is assumed that the drift will be really minimal across the nodes.
Yes. I mean, one is with hybrid clock mechanism, whichever nodes are touched as part of the message message passing across nodes, each message tracks that hybrid clock, and it will be I mean, it will be updated on each of the nodes,
So it will be
including the
synced-
client.
It will be synced when it travels.
Synced in the, yeah, I mean, hybrid clock is not synced in a way, but at least we talked about that causal relationship, right? So it will be monotonically increased across that message flow. The challenge is when that, let's say this whole transaction flow talk to only these two nodes, and then there is this third node which was not part of this transaction flow, and it still has, let's say, a record, and it still has its own hybrid clock, which is not touched by any of this, right? So then you have to rely on that transaction skew, clock skew guarantee, because there will be skew between this and this, and you can't really order. So if this is written at timestamp 10, and there is a value here which is written at timestamp 9, there is no way to really order these two.
So we have two stores, right? One is intent and one is committed. So
Yeah.
when the data is committed, it goes to committed.
Yes.
So when I do read, so
Yeah.
I directly go to the commit, right? So I don't have to resolve anything with the
You will need to, because there might be something that is already committed that this node doesn't know about yet, and then this read because in happy path scenario probably this would have been moved to the committed store already.
but then again, same question. If it is not committed, that means it is not successful, right?
No, but if it's not committed, then it won't be included in the read response.
Yeah. So for read, I can directly go to the committed code and I can read the data. So I can assume that, right, this is the final copy or latest copy of.
No, but then you will miss on transactions.
I will check.
You first need to check. Yeah, I mean, same reason why you do read repair, right? Because otherwise, though, I mean, you would miss on that update. So you can consider this. I mean, resolving intents is very similar to read repair. Cool. So I think tidy up that code a little more. I mean, essentially for that snapshot isolation. But the tests are there, and I think they are good enough to explore for learning. Yeah.
So I think the gap in understanding is slight gap is because in the commit, it's not necessary that always everything has been moved from the intent store to the committed store, because it doesn't wait for that.
It doesn't wait for
fire
that.
and
Yes,
forget.
yes, it's fire and
That's
forget.
That's why
Right.
It is a possibility. We are saying it is a commit, but
Yeah.
that doesn't mean every node has moved it from the intent store to the committed store.
Yes.
Yeah, that is the reason there is a slight
That is the
gap in
reason.
understanding.
Yeah.
Because we are, like, my understanding, and I think same for the person, that if we are saying it's committed, that means
Yeah.
everything is moved to from intent to the committed store.
Yeah.
So why we are
Okay.
why are we handling this?
But that's a very important point, because practically in any distributed system, I mean, including consensus implementations, in consensus as well, only one node, like leader, will know for sure when something is committed. If a client goes to a follower, it might have some entries which it doesn't know about. I mean, it doesn't know the result. So in that case, it will need to communicate to leader, asking it what is the state of this. So it is always the case. I mean,
So basically, you are saying we need to always handle for or design for such.
if you need latest data, yes.
Yeah.
Yes. Yeah, I mean, that's another caveat, that, I mean, you need to do this because we are assuming that we should not be missing on any strongly consistent. Yeah.
So are there any designs where we basically route the read to the leaders just like them?
Yeah, I mean, so here we are not talking about leaders, but in consensus implementations, if you want strongly consistent reads, they always need to go to leader. And even if they go to follower, the follower will redirect them to leader.
So in that case, I don't have to resolve the intent.
No, I think there you still need to. I mean, here there are no leader followers. That here, let's say, even if there is only one node, you still need to resolve the intents. Yeah, that replication example probably was confusing, but I mean, if you go to follower, you need to figure out if what the latest state is. Even in case of replication, that's what I wanted to. That's what I meant.
I think Zookeeper gives us an option, right, to read a string from.
Yeah. So all these databases. So again, it will mix the replication thing in here, but there are these multi-region replicas that they allow, right? And if let's say we are having a replica in India and another replica in say Europe, you can say that whenever requests come from European clients, they go to a follower in Europe, and it can happen that it's a stale data.
Okay, I guess that's.
Yeah, but you win big on the latency part. So in some use cases it's fine. In others it might not be.
Sorry, the earlier question was around the atomicity of the intent store and commit store.
The previous one.
Yeah, previous one.
Yes. Atomicity, like because we are moving.
In moving from so whatever I mean, so here in this implementation or what we're using for this exercise, it's basically the implementation of resolve, right?
Yeah.
So resolve will move from
that intent store into the commit store, and that needs to be atomic with that write batch kind of a thing.
Correct. That has to be atomic.
Yes.
Now here, of course, it is in memory.
Yeah. No, it's okay. How it is in memory?
Databases like in memory meaning okay.
Yeah.
Like basically it says MVCC store.
Yes.
Right? So now MVCC store could be a
in memory one
store
or a RocksDB one.
RocksDB
yes.
Store. In the case for RocksDB store, it will do the
write batch, put batch. Yeah.
Right?
Yeah.
So put batch is how it's
done. Yes.
Atomicity.
Yes.
So I mean, so suffice to say that all practical implementations will have
that
atomic commit.
Oh yeah.
Thing. So
yes. So the thing is that atomicity expectation is at multiple layers.
Correct. Yeah.
Right. So right now we are talking from client's perspective at this level,
correct.
But when any of the storage level primitives that are used, the expectation is that those operations are atomic.
The resolve operation
is atomic. Yeah.
And so whoever is writing the resolve operation will rely on
atomicity guarantee of RocksDB at the store layer. Yes.
To implement.
Yes.
So atomicity at the store layer, atomicity of resolve.
Yes.
What we are calling resolve
Here.
And leading to atomicity at the client.
Yes.
Basically the chain.
That's the chain. Yeah. And that's actually even true at the file system level, right? I mean, all the way down to the storage.
Right now we are stopping at the storage.
Stopping at that RocksDB kind of layer. Yes. But RocksDB internally must be relying on file system atomicity and yeah.
I mean, file system storage.
Storage, yes.
Storage level primitives.
Yes.
Magnetic disk or whatever.
Or SSD and
and whatever is that. Whatever is the primitive that the store layer, the physical storage actually.
Yes. Because there are so many complexities even at that layer. I mean, you might have heard of fsync gate paper, right? Because just writing to file system is not enough because mostly goes to the page cache.
It will go to the page cache. Basically, you
Yeah,
tell the
and even if you bypass page cache, it might go to the buffer on the storage
so
device.
You just tell the kernel. You don't
Yeah,
actually,
you don't.
You don't actually
Yeah.
go and
Right.
the kernel will flush.
Yes,
its
yes.
cache and
So a lot of databases nowadays use this ODirect API to directly write to the bypass kernel and directly write to the storage.
file
Yeah, I mean you still need that fsync to make sure that it's actually persisted. But there are tricky bugs that are found even in Postgres and other databases where fsync error codes were not handled properly. And fsync, when it fails, the expectations are not well known. I mean, what to expect, what happens to the page cache, and stuff like that. But we just limit ourselves to the RocksDB.
Yeah, I mean, at least for this exercise.
For this exercise, yeah.
Because that's our store.
Store,
layer.
yes, yes.
Everything, I mean, our guarantees are as good as
Yeah,
the guarantees that it offers.
yes. Okay, cool. Cool, so thank you.
The feedback forms and we'll take a group photo wherever you tell us.
Okay. Yeah, we'll keep the WhatsApp group active for a couple of days because whatever code changes I make, I will just update it there.